Buenos días, buenas tardes y buenas noches. Bienvenidos y bienvenidas todas y todos. Good morning, good afternoon, and good night to everyone. It is my pleasure today to welcome all participants of our international seminar titled Global Change, Risk and Perturbations on Social-Ecological Systems, Challenges for the Management of Coastal Areas in Chilean Patagonia. I'm happy to mention that we had more than 140 registrations from all over the world, including Canada, the US, Mexico, Colombia, Peru, Germany, France, and the UK, Australia, Uruguay, and also from Chile. This seminar has been organized by members of the Research Priority Area Team at the Universidad de los Lagos, including colleagues from the IMAR and CEDER centers. And it has been funded by the University Research Department. I will share my screen now. Okay. To learn and discuss about our topic, we have 7 national and international distinguished speakers today who are eager to share with us their expertise and, to the extent possible, to respond to the questions of the audience. As you probably know, we have a very busy program today. But before we go into the presentations, I would like to give a brief visual introduction and provocation to the kind of issues referred to in the seminar title and abstract. This map shows our region, the Los Lagos region in southern Chile, where we face the huge challenge of managing and governing multiple and overlapping activities carried on by social actors with different history, different interests on the coastal zone, its natural resources and biodiversity. Now I will show some of the layers that describe the social and ecological complexity at stake. First of all, there are more than 190 fishing coves or caletas, hosting more than 33,000 fishers, divers, and gleaners. They administer more than 300 turf-based management areas for benthic resources under a co-management scheme. There are more than 2,000 aquaculture centers in this region, owned by medium and large national and international companies, producing mainly mussels and salmon. As an example, if we zoom in to that box, we can appreciate the density of salmon farms in the inland sea of Chiloé. In addition, there are large-scale management and conservation schemes over the seascape, including 2 benthic plants, 65 marine and coastal areas for indigenous peoples, which are in different stages of application or approval, and also 4 marine protected areas. But the story does not end there. Over the past decades, we have faced a number of natural and human-driven perturbations on this ecosystem. And just to mention a few of them, the Isa virus affecting salmon industry, red tide affecting benthic resources and the artisanal activity, increasing eutrophication and pollution of the sea, and the decline of biomass. In a nutshell, you don't have to be a genius to conclude that under the current conditions and future uncertainties, it is more likely there will be many losers rather than single or few winners, unless we stop doing business as usual. Our role at the Universidad de los Lagos is to get involved in these challenges and to develop good and relevant science to contribute to understanding and solving regional problems. Therefore, the goal of today's seminar is to share evidence, concepts, and visions to guide our research and decision-making towards better responses to future risks and perturbations in the context of climate change. Just a quick note before giving the floor to our speakers. This is to the audience. Please use the chat window to write down your questions in Spanish or English. And we invite our speakers to respond some of them in the same chat. And at the end of each presentation, speakers will respond a couple of your questions that the team will select, because we will have some time for that. Nevertheless, all of these questions will be sent later on to the speakers by email, so they can reply and get in contact with the participants if possible. So, I would like to introduce now the overall introduction by Dr. Pablo Marquet from the Universidad Católica de Chile. Pablo, thank you very much.
Can you see my screen?
Yes.
Okay, thank you very much for Andrés for the introduction, and to Alejandro for organizing this global change and impacts on socio-ecological systems. As you anticipated, this is a region which sort of combines the best and the worst in a kind of a explosive cocktail at some point. So I'm going to try to, not to demystify the kind of pristine view we have on Patagonia, but just to try to unveil the complexity of the issues we're dealing with and how it changes from northern Patagonia to southern Patagonia. So one of the things that evokes, if you go into the Google and you do Patagonia landscape or Patagonia, well, you get two things. First is the brand, which actually occupies most of the space, but then you get this kind of wonderful landscapes of pristine habitats where you are kind of lean to actually go and see because they're so wonderful and pristine. So, but at some point it might happen that the trees that you see here might hide the real forest behind them. And the picture as I'm trying to, or will try to convey to you, is much more complicated than this pristine area. And in fact, there's a lot of things to actually urgently do in order to improve the resilience of this, because it's an area that has a lot of history, a long history of human influence. So let me start a little bit with what do we know about conservation and global change in Patagonia. One of the striking things that are very apparent in Patagonia is that it is kind of for humanity is very important. I would say because the first thing is that it's a huge water reserve area in the ice fields in Patagonia, and the other is because it contains a huge amount of carbon, which is being sequestered in the soils of Patagonia. Here I have a map of the soil organic carbon found in the first 30 centimeters of the soil, And you can see that Patagonia is a huge reservoir in Americas, one of the most important one, if not the single most important one, and with more than 200 tons, maybe an average of soil carbon on the soil. So it's something that we have to keep, and keep in the soil, not to go to the atmosphere, but one of the challenges is to keep it in the soil, actually, because of the action of fires might eventually send this to the atmosphere, and we don't want that, considering the climate change crisis we are facing. So that's one of the things Patagonia is well known for, and the conservation of this area is trying to protect biodiversity and these important stocks of carbon that it holds. So in terms of the conservation, one of the things that you have to realize is that conservation, at least of terrestrial ecosystems, is really impressive. You know, it really looks huge and wonderful in the numbers, at least. We'll try to dig a little bit deeper into how these numbers, what they do mean, and if the numbers are effective. But it's still, it's a huge concern that if you look at the distribution of protected areas in the country, you see the huge bias toward the south, but the bias is mostly terrestrial, it's not marine, and especially there is a very little representation of coastal areas in the marine protected areas in that zone. And here I'm going to zoom in to the south, and in the left, you'll see the kind of a creamy area is the terrestrial protected areas, and the blue polygons you see, not too many of them, are the marine protected areas. But the coverage of these marine protected areas, as you can see in this bar diagram, is less than 6% of these three ecoregions here, which is the Taitao here, the Kaweskar, and the Magellan ecoregion. So the coverage is really poor. But in addition to that, not only the coverage is poor, but also which actually it can be improved, and here is one of the great opportunities to improve this coverage, because if you see most of the terrestrial parks do have boundaries in the sea, so it's just a matter of extending those boundaries beyond towards the coastal area, and we will have a wonderful and very interesting way of articulating marine terrestrial protection as one important and single thing. That's one thing, but the other is the areas we do have, we have to strengthen the governance of those, and especially the budget to management, because at the point right now in terrestrial and in marine areas is really poor. I would say that's one of the main challenges for protection of Patagonia. So if you go, for example, today, a recent work by the Pew Foundation just says the diagnosis is very grim. Actually, it says that Chilean Patagonia has 113 full-time staff members dedicated to the parks, and so on average, each ranger have to be in charge of an area the size of Singapore. So actually, that's really kind of difficult to conceive, but it means that we need to strengthen the funding and the governance of the protected area systems in the area. Well, actually in the whole country, but it's really very kind of striking in Patagonia. So the terrestrial system is really kind of impressive. Protective system is impressive in terms of the figures, because you can, it's pretty much above all standard. It's like half Earth claims, you know, it's like 50% of Patagonia is under protection. But as with all figures, percentages hide a lot. So the question is, are the protected areas well located? Are the protected area where they should be? Do they provide coverage to all kind of conservation objects like species, for example? Well, the short answer is no. There is a lot of room for improvement, even in Patagonia. Here is a result of an exercise for Producer Pliskov. These are different scenarios for conservation. Just doesn't matter to go into detail what scenarios are there, but if you look at 803 species of vascular plants in the area, you'll see that if you do a conservation planning exercise and you ask what is the optimal distribution of protected areas that complement the one that we already have and jointly provide full coverage of all the species of plants that you have analyzed, and then you ask, or show me the 70% top of this, you will find that there is a huge, a large amount of conservation to areas to actually complement what we already have, and in order to protect all the species. But this is also true about ecosystems. So here is a map of the different ecosystem types in the area, and you will see that there is at least 2 ecosystem types which actually are underrepresented in this area, which are the steppes here and the deciduous forest in this area, which happens to be the most humanly dominated area in southern Patagonia. So there's a lot of room improvement. Protected area, interregional ecosystem is great. It's not the best, but it's great. It can be improved too, but we really need to know to expand the coastal protection, and there is an opportunity to actually capitalize on the fact that most of the terrestrial PAs actually go to the coast in order to expand protected areas toward coastal habitats. So, but this is it's good to have this, especially if you consider that some other drivers of global change are on the rise in the area, such as climate change. And quickly, I can show you here some of the predictions, some of the prediction for some of the. We compare 4 models only, and the sample they do agree with different kind of degrees of intensity that temperature will increase, especially in central and northern Patagonia, and that in those same areas precipitation will decrease strongly. But this will be actually very worrisome, because the trend so far, at least for terrestrial water storage, which pretty much is the ice field in Patagonia, has been decreasing very markedly since 2002 and 2016. This is pretty much satellite readings, and you see that this trend of reducing ice shields in Patagonia is really strong. So that's worrisome. And also, climate change will have impact on the species. And if you look at plant species and you project them to the future, you'll see that the diversity here is the present is to the left, and 3 projections, you will see that number of species will increase towards the south, no matter what the scenario is, and meaning that it's just the classical respondent species moving on latitude towards the south. So there's going to be a lot of changes are predicted. And also, the prediction is that extreme events will increase too in frequency here. As you can see that just by realizing that the deviation or the variability in temperature predictions and precipitation is higher in central and northern Patagonia than it's towards other areas. So, and already we have evidence that this is happening, and this is very congruent with other simulations, such as this one by Aguayo, a paper where René is also part of, and you see that the prediction for some river stream flow is at least in summer times, the predictions are that it will decrease. And to the right, you see that the probability of non-accident, so it means it means that the probability of having a reduction in flow is increasing. So that implies that stream flow is going to decrease, pretty much. So this will have a lot of consequences, as you will see. And one of the challenges for understanding human impacts in this area and the global change impact is that are all interrelated. We know that, but in this Patagonia, they are all interrelated in a very kind of strong way. And well, as part of this picture, as Andrés presented at the beginning, the human presence is increasing because there are more businesses, there are more kind of aquaculture is on the rise in the whole region, and so that's bringing more people towards the region, and also because of the famous national parks, the regional national parks, you see a lot of tourism going on increasing in the area. And here you have a graph of the number of hotel nights since 2014. As you see, for this is for northern in blue, central in orange, and southern Patagonia in gray. You'll see that the peaks are all increasing, and that there's a very strong kind of a summer signal, as you will expect from tourism going to the area. And this is correlated, of course, with an increase in number of people going to protected areas in both northern, middle, and southern Patagonia, and also an increase in the resident population of since 1970 towards 2017. You'll see the orange bar here is the middle central Patagonia, and the gray bar is the southern Patagonia, and both of them are increasing in time. And the blue is fluctuating. The blue is the Los Lagos region. You see is order of magnitude more people there. There was a dip in 1990s, but then it's now the trend is positive again. So there's more people, and the y-axis to the right is for the population growth rate, and is positive in all of them. So the trend is increasing pretty much. So you have more people, and that brings also changes in land uses, and what is more worrisome, a decrease in pristine area. Even though the other land uses are not dramatically increasing, there's a decrease in pristine areas, as you can see here in these graphs, pictures from 1930s. Each column you follow down is the time increases for all these different land uses for ranching, pristine, and regeneration. You see that ranching is becoming yellower, so is increasing in proportion. Pristine is becoming also yellower, which means that going from red, which is a high proportion of pristine, it moved towards a lower proportion of pristine, and the projections are that this curve here, which is the proportion of land in this land use, which is pristine, will go down at least until 2070, and then will stabilize. So this is kind of a coincidental with this kind of analysis that shows that different indices of human disturbance in southern Patagonia generate similar results. At least the top two ones and the human influence index show that there is a strong modification of Patagonia. At least 53 to 68% has some degree of human intervention. So pristine Patagonia, no more. We have a highly intervened area, and the kind of a remaining pristine areas are all located along the coastal and fjord ecosystem. But the other parts are kind of heavily introduced. And one example of them, for example, one of the negative consequences is the peatlands impact, which is another reservoir of carbon. And peatland has, I will say the last 2 decades, they start being heavily impacted by human extraction of the mosses or the sphagnum, because it has a high price in the Asian market. Hopefully, there was a last year, I think it was, that there was this new law that established that if you want to exploit this, you have to have a plan, a management plan, and to assure its long-term persistence. But this is not only the negative impact that increasing human presence have in the area. It's also associated by a long time presence of exotic species that I don't want to talk too much about this because everyone knows that it's very strong. I just want to be pictorial, and this is two pictures, one in 1940. This is a British man kind of fishing for brown trout in Nahuelhuapi Lake, and to the left is a student of Universidad Austral who actually caught this huge specimen of Chinook salmon that probably escaped and it was wandering around the rivers and eating up all the small native fish species which have been pretty much decimated by all the introduced ones. So we know a lot about this kind of impact, not too much in the terrestrial, but a lot, I mean, in the fresh water, we do know a lot, but what we do know the most is on terrestrial. And there is a gap in knowledge in terms of the marine kind of understanding of invasion. So marine invasions are kind of going very silently, and that might be very dangerous too. So as summarized by Andrés on Venezuela, 2014, most studies have been located in terrestrial habitats. This he's talking about invasive, and very little one is on the marine. And the same is true for reanalysis done recently by Martinez Harms, where you see that terrestrial here in red is the largest number of studies in terms of impact of global changes in Patagonia. So speaking of terrestrial, there's a huge problem with terrestrial because they do seems to affect each other positively. So beavers and muskrat and American mink have positive impacts on each other, and they kind of have positive impacts on other exotic grasses and other exotic fish species. So it might be ground to claim eventually an invasion meltdown in Patagonia. So, but this is very complex because there is a large web of interactions, and we are not very sure on all the linkages and how strong they are. So, and needless to say that, as Nelson pointed out, or just pointed out at the beginning, aquaculture of exotic species on the rise in northern, central, and southern Patagonia. And this brings us to one of the all these impacts: exotic species, changes in land use, and climate change start interacting with each other, and they manifest in terms of in Patagonia. One of the hallmarks of these changes is harmful algal blooms, which are also on the rise. And this started kind of illustrating the complexity of all this, because somehow one of the important species behind these blooms is Alexandrian catanella, which is a dinoflagellates that is moving. If you look at the time extensions of it, influence is moving north, and Pseudocatanella verruculosa, which is a microalgae, is moving south. So together they are kind of encompassing the whole area with nasty consequences, and especially when some climatic signals or the climate is propitious, which is when, for example, when it happens in 2016, that the dominant kind of weather variability modes, which is SAM, which is the southern annular mode, has a positive phase, as well as the ENSO had a positive phase during summer, bringing a lot of high temperatures and dryness, which actually generated very nasty consequences and actually propelled the intensity of this bloom with nasty consequences on other parts of biodiversity, like a lot of whales were stranded in in coastal Patagonia. Not that the stranding whales are not seen before. Here is a report from 1968 to 2020, where you see there is a lot of stranded marine mammals along the coast. But the number and the intensity of the episodes have increased. And the most recent one reported shows that there were 343 stranded sail whales primarily in the area associated to high productivity areas like shown here, which is kind of blooms where all these blooms were concentrated. And here you can identify the whales from aerial kind of pictures, all the stranded whales on these beaches, and they have, some of them had toxins from the blooms of algae. So algal blooms can propagate up and down the trophic kind of food web. But this is only one of the major emergent kind of hallmarks of global change in Patagonia. The other is changes in the fire regime, and fire is on the rise, unfortunately. And since, I mean, late glacial times in northern Patagonia, the evidence suggests that after a very cold last glacial phase, the weather became more mild and hotter a little bit, which actually fostered the increase in vegetation, and trees created good opportunities for fire to increase. And also after 5,000 GVP, a strong El Nino influence on northern Patagonia actually created better possibilities for fire. And this is pretty much El Nino bringing moisture on winter time and kind of bolstering productivity and generating more fuel for later season fires to sprout. And the other impact here is the European presence back in the 1800, and since then there have been an increase in fire, which is very apparent in the southern part of Patagonia, actually, where you can see, this is one study by Mundo et al., where they date all the scars of trees in forest, and they kind of, through this dating, they can reconstruct, at least for using this Notophagus forest, they can reconstruct the history of fire in the region. And here I'm showing you just a glimpse. You can see the frequency of these little dots increase as you go from 1700 to the present, and that the proportion of trees with signs of fire also increases, and the frequency of fires do too. And to the right, you see the panel where the top panel is the number of fires, and the panels behind, below it are associated with the increased population density in the area. So you see an increase and a dip in population in fires when also the population growth rate decreases. So in general, there's a very strong association of human being kind of responsible for the increased frequency of fire, in addition or in synergistic kind of interaction with weather patterns. But the weather pattern that is most influential in this area is this southern annular mode, which is positively correlated with increased temperature and decreased precipitation, and also increased number of drought events, which is what this SPEI 6 measures. So here's a picture of you have the ENSO impact and the SAM impact, which interact with the human impact in the area and can generate from algal blooms towards increase or changes in fire regime. So that's a picture of what we know, but there is some things we know that we don't know, and I'm gonna kind of talk a little bit about that. And one of the things that we don't know is that we know this is complex and these things interact with each other, all these exotic mammals, but we don't know if you put all the other exotics, how the picture will look like, because they do interact. Bombus has Bombus terrestris, this thing is this pollinator is having a very negative impact on native pollinators. We have Didimo on the river, we have hares and rabbits coming in, but more worrisome on the fire regimes are these two species, Pinus contorta and gorse. Gorse is everywhere in Chiloé Island. You can see it from the sky because of the yellow kind of flowers. It's moving everywhere, and both of these species are flammable, highly flammable, and they have a risk for the rest of the ecosystem in terms of making it more fire prone. If you add to that the climate change impact, then the picture doesn't look very nice. And also the other two typical kind of companions here, feral dogs and domestic dogs and feral cats that actually pose a large threat on local native species. And just to expand on the complexity of this, let me share with you this. I think it was done by René Garreaud's daughter, which is an artist very committed to putting in pictures what the dad does in print the papers. And he made this figure, which I really like it because it's a wonderful one in terms of showing all the interrelationship between different components on land and on the sea. And what this is a way of explaining, this is a paper by Leon, who actually, and Garreaud, which they show that what happened in 2016, it was a positive phase of the ENSO, but it was summer, increased temperature, and it was a positive phase of SAM, which also increased temperature and decreased precipitation, that decreased the river stream flow, which actually relieved stratification, which actually made possible for the deep nutrient-rich waters to upwell and generate more nutrients availability for this macroalgae, and also aquaculture inputs of nutrients and high temperatures created the perfect condition for high growth rates of this phytoplankton that created a very difficult situation for the aquaculture industry and for humans in the area and for other biodiversity components of the system. So this was one of the extreme events that we unfortunately believe there is good evidence to show that they will increase. This is a Diffenbach analysis of extreme events in terms of the driest year. So you see Patagonia here has a kind of a increased ratio, and the same is happening in northern Patagonia with long dry spells. So the weather is going definitely get drier, and the condition for algal blooms probably become more likely, and the condition for forest fires also becoming more acute. So this is a complicated picture, but there is hope. Somehow we have hope. There are some positive things, and I just want to point out some, just not to finish with such a terrible kind of a message. One of them is in the whales. I like whales, and whales are very important in ecosystems. Not too long ago, we learned that there was a concentration of blue whales in the Waffle Island near Chiloé. These are tracks from whales migrating from Galapagos area towards Chiloé, where they have a feeding ground. Unfortunately, whales were decimated in Chile since 1905 up to the present, up to 1983, when whale industry went off. In Chile, there was at least 50,000 specimens were removed, killed by the industry, not counting all the Norwegians industry fishing, which actually they had a whale camp in Waffle Island, especially dedicated to harvesting the blue whale. So whales are very important. We have come to realize, not only because they provide mixing to the ocean, but also because they eat down in the deep and defecate up in the kind of a photic zone generating or sending a lot of nutrients that can create increasing phytoplankton productivity, and that's fixed carbon. So that's why they represent a kind of a nature solution to climate change. And a healthier population of whales will improve the ocean health and will also kind of provide a way of sequestering carbon. And when they die after a long time, actually they are equivalent to very long trees on land. They sequester like on average 33 tons of carbon that it goes down to the seabed and actually can get sequestered there. So a healthy population of whales will bring a lot of benefits and will also serve as a parachute to protect other coastal areas of Patagonia. But not only that, let's also remember the important populations of brown algae that are also part of blue carbon that can be very important to sustain. So just to finishing up a couple of remarks. All systems are interconnected. Somehow what happened in Patagonia is that everything is highly connected in a very kind of reduced area. So you see, and it's very apparent, the interconnections and the cascading effects of disturbances on this ecosystem, which already have a long history of perturbation. So it's not as pristine as we usually think of. Also, there's a strong concentration of this impact somehow. And the other remark is like you are left with the feeling that everything in Patagonia seems to reach epical proportions. Not only living there for the first colonizer, but all the propagation of impacts. The algal blooms are huge. All what happened to the whales and fires also is kind of epical in proportion. So hopefully they will not become epical in the wrong way and become more kind of more control. So in order to bring control to this, or resilience to this ecosystem, we have to be very highly aware of the interactions among the drivers of global change. And one of the things that emerged as low-hanging fruits is the creation of well-founded and managed marine areas, and also the kind of expansion of terrestrial protected areas toward the sea, along with management of invasive and especially fire regimes. And we have to also keep in mind the importance of these ocean-based solutions that are really kind of important and can bring conservation on the parachute of actually abating climate change for the region. So this being said, I just have to say thank you very much for the invitation. And if there is time for question at the end, or I don't know how we're going to work, but thank you very much.
Thank you very much, Pablo, for this interesting, thorough, and deep overview of Patagonian scenario in terms of biodiversity. We have still a long program to go through, and we will have to go directly into the first specific chapter of the seminar, which is governance of social-ecological systems. And I'm very happy to introduce now to Dr. Fikret Berkes from the University of Manitoba in Canada, who has already recorded his presentation, and we look forward to hear it.
Hello, everyone. My name is Fikret Berkes, and I'll be talking about social ecological resilience for local to global governance. I've been given a question. What is there for us in southern Chile to learn from your experience on how to govern a complex coastal area with intensive and overlapping uses? Of course, my first reaction was there are many crowded coastal areas with conflicting uses, so that's not really unusual. Example that comes to mind is Southern California, where I won't go through the whole list, but you can see a huge number of uses, leaving, in fact, very little space for anything else like fisheries. On the other hand, there are positive and constructive views of coastal resource use. This one is the Japanese concept of Sato Umi, and it shows a harmonious relationship of urban uses, industrial uses, fisheries, aquaculture, recreation, and so on. Incidentally, this concept was used in the restoration after the horrendous earthquake and tsunami in 2011. The plan of presentation is as follows. I'm going to talk about social ecological systems and resilience, and then I'm going to talk about communities and local actors in the context of multi-level governance. Then we turn to adaptive governance that includes social learning. And then I say a few words about participatory research methods that help build resilience. The social ecological systems idea is quite simple. The argument is there are no pure ecosystems in the world. We all live in human-dominated or at least human-impacted ecosystems, so we should be looking at not just ecosystems and ignore people, but we should be looking at an integrated, intertwined social subsystem and an ecological subsystem, making up a connected, interdependent and co-evolutionary relationship, and that's what we call the social ecological system. We're talking about social ecological system resilience as the main topic, and it's a systems concept because the two parts of this SCS are connected with feedbacks, many kinds of feedbacks. But the original resilience as conceived by Buzz Holling, the ecologist, what was it? Was just an ecological system. But since about the year 2000 or so, we've been talking about the interconnected social ecological systems as opposed to just ecosystems. Can't get into this now, but all the various characteristics of complex adaptive systems come up in some form or another: scale, nonlinearity, unpredictability. And we focus on drivers of change, which are basically disturbance events, otherwise worded. And we're dealing with biophysical drivers such as climate change. Obviously, it's a major theme at the conference here, but we're also dealing with social change drivers such as government policies and global markets, which impact what coastal resource users do. A formal definition of resilience, I'm using the one by Brian Walker and colleagues, including Holling. And it's the capacity of a system to absorb disturbance and reorganize while undergoing change. But the system still retains essentially the same functions, structure, identity, and feedbacks. In other words, resilience is not about a fixed system. It's not about going back to the original. It assumes change, but maintaining its integrity while undergoing change. So when we say a system is resilient, we mean it has the ability to absorb shocks and stresses. It can self-organize because it has social memory, which allows it to start the cycle all over again. And it has the ability to learn and adapt. Now, a word of caution. Resilience in social sciences is not particularly well developed. It started as an ecological concept. It is a systems idea. Many social scientists are not entirely comfortable with this kind of approach. And resilience basically doesn't or has not really done all that much in terms of power relations, in terms of agency, in terms of equity. We're still working on these. But the systems concepts in resilience are very well developed indeed. And two of the important ones are thresholds, which are the tipping points, where you have one system flips into another system. It's a system transformation. That's when ecologists or when resilience people say transformation, they really mean a flip of one system into another. But also very important is uncertainty. And a quote from Ann Kinzick and colleagues to a report to National Science Foundation in the US points out that social and ecological systems are sufficiently complex so that our knowledge of them will never be complete. So we cannot use the cop-out of saying we need more research. There's essential uncertainty, essential unknowability in ecosystems and social systems. Now, what does social ecological resilience include? We ask the questions, is the system coping with change? Does the system have flexibility to adapt to change? And does the system have the capacity to transform? So the intensity of change, or if you like, the degree of perturbation is really important. So the overall relationship looks something like this. Resilience in the more recent years is considered to include the coping capacity, which is about stability and persistence, adaptive capacity, which is about flexibility and incremental adjustment, and real big change, which we call transformative capacity. So I'm following Christoph Benne, Kate Brown, and others in looking at it this way. But the original Holding Resilience, if you look at some of the earlier literature, resilience is basically equated with adaptive capacity. Of course, the two terms come from different disciplines, so they're not exactly the same. But Holding hated the idea that resilience can be equated with stability. But the new notion that I'm using about resilience does include the coping, which is basically trying to remain stable. Now, we move to governance kind of issues. Suppose you have a coastal area with intensive and overlapping uses, as the question posed says. Our practice has been to start with the community. That's not the approach everybody uses, but that's the approach that I've been using with coastal resources and small-scale fisheries. I start with the community because it's the lowest organizational level, and so we deal with the community or major social actors. You may have aquaculture, for example, which is not necessarily part of the community, but it's a major local actor. When I started working with communities, we were initially talking about community-based management, period. But over time, of course, it became obvious that community-based management cannot be complete in itself. It's a necessary condition from my point of view, but it's an insufficient condition because we live in a multi-level world. There are all kinds of other influences that impact the local level. So we need to look at linkages. So the next step in the analysis that I've been using starts with the community and local actors, but then it looks at linkages. Because complexity theory, after all, says you have to consider all levels together. You can't isolate levels and deal with them one at a time. So when you look at linkages in a multi-level governance, you have the community, and you have several communities which can link to one another. And these link to regional, if there is a regional level of organization, and they link to national, not necessarily to global, but often it's important because some of the policies are at global level, that economic drivers also can get at global level. Now, we talk about vertical linkages, which are these dark arrows. And note that they're two-headed dark arrows. So it implies two-way communication rather than the usual top-down, where the government tells the communities what to do. So good linkages, in the way we've been looking at it, are two-way exchanges. Horizontal linkages, not shown here, but those are the levels among actors at the same level. Communities interacting, fishing unions in Chile interacting, and then you have the regional level, different regions interacting. The significance of this linkages in multi-level governance is that if you don't have the linkages, something that happens here cannot be communicated very well to the national level, or something that happens there doesn't filter down too well. The way Simon Levin puts it, you need tighter coupling of these levels so that the change and response can also be tightly coupled. Now, of course, the schematic diagram I showed oversimplifies things, just to make the point that local actors themselves can have complex networks. This is the Chilean coastal management system for benthic resources. It's taken from the thesis work of Andrés Marín. So I'll only point out that you have the different fishery organizations. Each circle is one, and there are two regions, region 1, region 2, and they have huge number of links to not just one cluster of players like government or two clusters of players, but actually 7. And if you have more detailed questions on this, good thing we have Andrés Marín here, because you can ask him. Now, we do use the simpler schematic diagrams, and I want to make 2 points here. One is about social learning. The networks is where social learning occurs. It's a collaboration of the players. It's feedback-based problem solving, and people and organizations really do learn. Learning is not just an individual phenomenon, as education people often tell us, but there is such a thing as social learning and institutional learning. The other thing is networks is where the social memory resides. Social memory are the elements of the social-ecological system that's important for self-organization and renewal. So this is really important. The example is from Sweden. It's a biosphere reserve case, and what it shows is that a co-management body here called EKV, the Eco Museum, brings together players from the conservation area, players from the water quality area, and players from cultural heritage. Now, not all conservationists are interested in co-management, so you only include those players from that cluster who are interested in coming together with others to solve a problem. And this is what the network accomplishes. Now, governance. Step back a bit. We're using governance as the broader area in which institutions operate. It's the more inclusive term than management. Management is about action. Governance is about politics. And note, we've had a major change, if you like, major change in the social contract. We used to say government handles it all, not anymore. And this is the case in Canada, in Europe, in Chile, definitely in many other places where Governance is not only for government managers, but in fact, governance involves other actors, as in public-private partnerships, which is government partners and private partners, or co-management, which is government partners and local resource user partners. Moving into adaptive management, we're talking about social learning so that management can learn and move on and adapt. Conventional management doesn't have that feature. The conventional management, the management as we've been doing in the 50s, 60s, 70s, to some extent 80s. One of the problems ecologically is that it has assumptions of equilibrium and controllability and deals with only one sector at a time. These are bad assumptions, and of course single sector at a time doesn't work. So what we do need is ecosystem management, which looks at all the sectors, but ecosystem management as practiced now is still short on being interdisciplinary, and it's still short in many cases in addressing the full social ecological system relationships. So we need to move from, we retain ecosystem management, but we need to move to adaptive management, adaptive governance. And that, the main point here is the feedback learning in the system, and in particular, taking uncertainty into account. That becomes important because it's part of the argument for collaborative approaches. Unpredictability of complex systems means that our old conventional way of expert knows best conventional science is not going to work well. So we need collaborative approaches, we need cooperative approaches like co-management, and we need partnerships not just in an information top-down information transmission sense, but we need partnerships in a sense of deliberation. That is, we discuss the important questions together, we discuss research approaches, we carry out the research, and then we also discuss and take action on the meanings of the findings. What do the findings tell us, and how can we solve the problem together? So it's very different from using the top-down government expert knows best kind of approach. Knowledge co-production comes up a great deal, and this is about bringing a plurality of knowledge, including fisher knowledge, including aquaculture practitioner use knowledge to address a defined problem. Why are we getting disease problems out of aquaculture operations and so on? So these collaborative approaches are basically about learning together so we can move on and do better. And it's facilitated by good leadership, always important, and certainly having networks of partners. Now, there are some issues of social responsibility. As a researcher, I've tried to address these. And the idea is that researchers can actually build resilience. They can help build resilience. There are methods of applied research that help build adaptive capacity and also address power asymmetries. I've been working with indigenous people a great deal, not just in Canada, but internationally. So we have community development, community-based planning, as I've done with Helen Ross in Australia. And there are a number of participatory methods that can be used. I can't go through a full list, but I'm going to mention 3 of these methods. And the idea here is to help communities increase their own understanding of change through research, reflection, and social learning. I'm going to mention capacity development, participatory research, and participatory scenario planning. Capacity development we've undertaken in a project in Brazil, and we work with local organizations of of fishers and tourism operators who are in negotiation with the government because of large marine protected areas. Initially, the local actors found that they couldn't even follow the language that the government people were using. So we do all kinds of exercises to first get them familiar with the terminology and the approaches, and to develop new approaches that they can use in negotiation. Okay, so that's capacity development. Participatory research, the example here is from Uruguay, a PhD work of Uruguayan PhD student, Micaela, and this is research in which the community sets the objectives. The research is carried out jointly with fishers and scientists, and also involves public engagement, because the idea was to give a higher profile to small-scale fisheries. So the fishers basically did an outreach, and we've done similar projects in Canada, and they don't work very well, but they certainly do work to some extent, and participatory research is an important tool. The third one is participatory scenario planning. This is in the millennium assessment sense, not in the climate change scenario sense. These are simple scenarios. You pick two axes, two variables that the local communities consider important, and then you build basically a 2x2, 4 scenarios out of that. The example is from Kenya, from the work of Tim Daw and colleagues. A small-scale fishery at Nyali near Mombasa, and they generated 4 scenarios. Now you can use simple, these are not quantitative scenarios. You show the scenarios as narratives or artistic representations. In this particular case, artistic representations, scenario A, B, C, and D, which are used with the local community to generate discussion as to what is desirable and what is doable. So finally, we go to the third item in resilience, transformations. In the Kenya example, actually, scenario C and D do show transformations. One is about mass tourism, scenario C, and D is where the small-scale inshore fishery becomes a larger-scale offshore fishery. In practice, transformation becomes necessary when coping and adapting are no longer possible, that the system as a whole has to transform, let's say, from a fishery to a recreational industry kind of area. And we have many examples in the book called Governing the Coastal Commons. There's another interesting angle, the political ecology angle of transformations. Transformations can be about local empowerment, not just the physical transformation of the economy. And it can be a change in political relationship, and as such, transformations can be used towards a new social contract. Conclusions. Going back to our question, what's the international experience on governing coastal areas with overlapping uses, conflicting relationships? Well, our experience is that a holistic view is definitely important, and it helps deal with perturbations and change using the social-ecological systems as the unit of analysis. Resilience thinking is appropriate for dealing with change. It's one of the major tools. It's not the only theory for change, but it's the one that we've been using. And resilience allows us to ask questions about whether the system can absorb shocks and stresses, whether the system can self-organize, learn, and adapt. And although this is a bit reductionistic because it's really a continuum, as the figure showed, resilience is really the sum of coping capacity which turns into adaptive capacity as the intensity of perturbation increases, and finally to transformative capacity. Now, another caveat, resilience is not a cure for all, and not all kinds of resilience are desirable. Gangsterism comes to mind, corruption, political corruption comes to mind. It's very resilient. You can't get rid of corruption. It takes many generations or never to get rid of some of these things. And so resilience is a neutral concept. It can be good or bad. But what you do need for coastal management, you do need the multi-level links between the various levels as well as the horizontal links, so that communities can communicate, different local user groups, different local actors can communicate. And to move into adaptive governance, you do need social learning. We don't have terribly good examples of adaptive management, let alone adaptive governance, but we have elements of it in various cases, in various places, including Brazil, including Canada, including Chile. And social learning and collaborative approaches are important, and they do help manage coastal conflicts. And we do have tools and applied research to build resilience. We can develop capacity, we can do participatory research, we can use simple scenarios. And these methods help communities and local actors to increase their own understanding through research, reflection, and learning. Thank you.
Thank you very much, Dr. Berkes. We are happy to have you here as well, connected. Can you hear us?
Yes.
Oh, we can hear you too. Something that all of us are missing from the pandemia context are the applauses. So this is mine for you. We have still some time for questions. We received the following one on the chat. How do you cope with changes within the actors at the different levels? Meaning every time you have changes in the government or locally, for example, those linkages might get interrupted. It might seem you need to start up the interactions over and over again. Can you share with us a few thoughts about it?
Well, thank you, Andrés, for the easy question. Yes, perturbations will interrupt governance relations. It will interrupt linkages. And that's why in co-management, it's a good idea to start with easy problems, relatively easy questions where most people can agree on, and basically work up build up a working relationship. So that's key. If you don't have a working relationship that involves some of the members of some of the parties, you just don't get anywhere anyway. So yeah, so building those relatively easy to make connections, linkages, tackle some problems. Some actually mentioned by the last speaker, like red tide, obviously has to do with nutrients at the wrong time of the year that the dinoflagellates can use. That's maybe it's not a terribly good example of an easy problem, but it seems to me easier than some of the other problems.
Okay, thank you. There's another one that will be probably interesting for many people in these and other areas where there are many indigenous communities and resource users. You work a lot also with local ecological knowledge and traditional ecological knowledge around the world. Have you found any indigenous concepts or worldviews or notions that somehow refer to the scientific concept of resilience? Is there, if I interpret, if I get the question right, is there hope to bridge our scientific understanding of resilience with some understanding of local communities so we can build some dialogue together?
Well, there are no indigenous terms for resilience that I know of, not in Canada, not in the Andean region. But of course, there are concepts. The Andean people, not in Chile, I guess, but in the central and northern Andes, the Pachamama idea obviously is one of the ideas from the Mother Earth idea. Comes from indigenous people of the Andes, and Ayulu, the idea that people and other elements in the landscape, animals, plants, spirits, are all part of an interacting family. So these are holistic concepts, not quite resilience concepts, but I think for the marine planning, I'm not sure your indigenous people are marine users. There are certainly mountain type people involved. I don't know what the coastal people do. I just don't know enough about your indigenous people in this area to be able to really make a comment on this.
The final question. How can social ecological systems thinking and research actually integrate with political science to improve sustainability?
Well, it's a starting point for sustainability. The ecosystem view. The previous speaker gave a wonderful overview of all the things that are known and maybe not so well known. And you need all of that, including the human element, including the governance element, which is what makes it social ecological system. And then move on to sustainability with this, the background of the large system in mind. Obviously an overview of all the drivers as well. And that makes a very complex system, but resilience has what Buzz Holling used to call rule of hand, meaning there are usually 5 key variables, 5 fingers. So you tackle the biggest variables in the system as a way of handling complexity.
Thank you very much, Dr. Berkes. Feel free to mute your microphone now, if you want. Now it's time to move forward to Dr. Stefan Gelcich presentation from Universidad Católica de Chile. We have invited him to bring down some of these broader concepts down to the Chilean context and show some of the results he has obtained from years of research here in Chile. We go for it. Hi, Stefan.
Good afternoon. Today I'll talk to you a little bit about our experiences here in Chile trying to integrate research on social and ecological systems in coastal zones. I decided to start with this slide. Welcome to the Anthropocene, planet dominated by humans. Just to remind ourselves that the Anthropocene includes the oceans, but more importantly that humans are more than just drivers of ecosystem change. They're also part of a social system that interacts with the environment. And under that context, the question I received from the organizers today was, what can we learn from social ecological research experiences in Chile on how to improve management and governance in coastal areas? So what I decided I was going to try to do is ground that question in experiences and lessons in two main systems. One is the system of artisanal fisheries of benthic resources in Chile, where I want to try to assess responses of fisheries co-management policies and how this type of research can inform the continuous design of innovative resource management strategies. And the other thing I wanted to do is ground it in mussel aquaculture and tell you a little bit about our experiences with social ecological research, trying to assess the impacts of global stressors, specifically ocean acidification, and trying to explore the adaptation potential of the mussel industry in the country. And so I'll start first with the benthic artisanal fisheries co-management that we have in Chile. It takes the form of what are called management and exploitation areas for benthic resources. This is an article in the Chilean fisheries law that grants territorial user rights to fisher associations in what are called these turfs. This is a co-management system between state institution and fishers, which is supported by technical institutions or universities or consultants. Of course, fishers must comply with a series of requirements to be granted one of these territorial user rights. They have to develop stock assessment studies with technical consultants. They must have an approved management plan by the authorities. They have to enforce their areas. This is just a little picture of one of these enforcement shelters. Here's a picture of an idealized turf system in the little red dots. And this is the type of fishing boats for benthic resources along the coast of Chile. The first turfs were implemented in 1997, and along the country we have around 450 fully operational turf areas. What is pretty interesting in my opinion is that as we have so many turf areas, there's also a lot of heterogeneity in turf's performance. What I show you in this graph is just the result of a meta-analysis of studies in the last 25 years that have assessed turf performance compared with open access areas. So in the graph, what you see towards the right is because one of the different ecosystem services is more abundant, more present in the turf. If the little dot is on the left, it's because it's more abundant in open access areas. If the error bars touch the blue line, is that there's no significant difference between these. Okay, so this graph shows the results of 33 studies over multiple ecosystem services that compared turfs with open access areas for, in the light green, provisioning services, so mainly food production. Within the food, mainly a gastropod named Loco that is very important in the turf system because of its price. In the darker greens, supporting services, there's mainly of biodiversity in these in turf areas versus open access areas. And in red, regulating services, mainly as larvae production or reproductive potential within turfs compared to open access areas. Okay, so as you can see, there is heterogeneity. Some turfs work better than others. And of course, there's multiple factors that interact to provide those results. There's environmental factors. If you're in upwelling areas, non-upwelling areas, there's more productive areas than others. There's also socioeconomic factors, cultural factors. What I'm going to do now is show you an example of some of the factors that can determine performance and through which we've been also learning in terms of trying to tweak the policy. So one of these factors might have to do with social capital. Okay, social capital from a network perspective represents the stocks of relationships. So under like a social capital hypothesis, higher social capital would be associated to better performance of turfs. And we've done this, we've tried to test this for ecological and economic performance of turfs we could have. So if this is a governance network of the turf system, and the little dots in the middle, the gray ones, are different fisher associations, okay? And the size of the symbol is just the net facilitating degree of this governance network. The colored dots around are other important actors in the governance of turfs. So as you can see, it goes way beyond just the state and the organizations. There's a lot of other actors involved. But for what I want to show you today, from this network, okay, from all these lines that link different fisher associations between them or link fisher associations with other actors in the governance network, we can calculate some indexes. We can calculate some social capital indexes. And what we did here is calculate some linking social capital indexes and bridging social capital indexes. So the linking ones relate mainly to the relationships between fisher organizations and other levels, other actors in the system. And the bridging one relates to the relationships between fisher organizations. Okay, so as you can see, there might be organizations that have high linking social capital and high bridging, others might have high of one, low of another, etc. In general, our results showed here that linking social capital is more present, but that both are important to determine outcomes. We think that the increased linking social capital is due to the way the policy has been implemented and supported. That very much depends on fisher associations having relationships to other levels of governance, the Undersecretary of Fishery, funding agency, authorities, etc. Linking social capital is related to the ecological performance, but both social capitals are important for the economic performance of these terms. Okay, so at some point there must be some work done on understanding and developing these bridging relationships. Of course, it's not only linking and bridging relationships that are important for fishermen groups and for the policy. We've also estimated the role of bonding social capital and leadership. Bonding social capital are the internal relationships within the association. And here we also use multidimensional outcomes to assess performance. And we found out that engaged leadership and agreement around sanctions are the ones that really best explain the outcomes of these bonding within the organization unions. So we've begun unpacking these pro-social elements that are confounded under like a big word of social capital, and that also allows us to explore further and maybe start developing programs to support some of these important elements. Of course, there's different ways to understand drivers. That was only one example that comes from social network analysis, where we've learned from. This is another example just based on surveys about problems in turfs. We did around 560 surveys with fishermen from 55 associations. Individual fishers still feel that the main problem with the turf is poaching. 72% felt that. In the leaders, 90% of the leaders felt poaching and price volatility are some of the main problems with their fishing associations. So what we've tried to do based on that is assess the vulnerability of fisher associations to two main problems: price volatility and poaching. We did this sort of with an idealized IPCC framework. We have exposure, sensitivity, different dimensions of adaptive capacity to measure vulnerabilities. What's interesting is that we're measuring vulnerability to different stressors, in this case, markets or poaching, or some general aspects of vulnerability. This allows us to map specific vulnerabilities to poaching and market volatility, and also some generic aspects of vulnerability. Through this, we can prioritize vulnerable geographies, communities, or sectors. As you see in this bottom graph here, we can select some fishing associations that are more vulnerable, in this case, to poaching. These two very vulnerable to market volatility. Work upon that, see what happens with that. Eventually, with this type of framework, we could also start integrating climate change data. Of course, once we're confident on the data at these scales, we sort of know that the variability in some of these data in coastal zones is very different, for instance, of ocean acidification to other places of the ocean. Okay, the big challenge here is still how to build adaptive capacity at community and individual levels, or how can this governance system continue evolving to build resilience for these fisher organizations. And this is where I think that one of the main lessons that we've been learning come, and it has to do with the need to develop these types of niche innovations, these novel ways of viewing problems, what I like calling learning platforms. This is just one that I'm going to show you here. That is a program with artisanal fishers that compensates them for the opportunity costs of setting aside a portion of their turf as a no-take zone. So if this is their turf, this is the fishing association in town, open access or de facto open access areas, there's a no-take zone there. The outcome of this program should be a scalable program that provides supplementary revenue to fishers in exchange for management actions that can produce verified and enforced biodiversity benefits in these areas. This is actually very important also to be able to have some conservation in areas with multiple uses, etc., that engage fisher participation. Today we have 3 of these turf reserve programs going on as learning platforms. We've developed the enforcement technology for these areas. That's one of the big problems. I don't have time to go into it, but I can send it to you. We've developed the market model, financing schemes. We now know the trajectories of biodiversity change. We've managed to include some machine learning with the cameras to help enforcement. And we've worked quite strongly on the scalability of the program. Okay, so we've actually managed to build the most and least desirable program from a fisherman's perspective in terms of what attributes of the program. What is the broker identity? How long are the contracts for? How much money must be involved? What type of enforcement we need? These small design choices, now we know we've constructed them together. And if this is the participation probability for different payment schemes, if we put all the attributes that we didn't know were the non-desirable attributes together, this is our participation. It doesn't even get to 50%. But if we put the desirable attributes in terms of who the brokers are, etc., we can actually get predicted probabilities of participation that are over 50%. These predicted probabilities could be larger just because of designing the system well enough, more than because of the payments. Anyway, what we've done here in these learning platforms is trying to integrate multiple knowledge and learning systems in an adaptive way. I really like this photograph. This is a leader of the Fishermen Association. This is where we present the turf reserve, and these are state institution representatives working together in how to push this forward. Here again, presenting in a television, regional television show, this idea of fishermen doing no-take areas. More importantly also, I think we've been advancing in principles for knowledge co-production. So when you get involved in these learning platforms, They have to be context-based, pluralistic, goal-orientated, interactive, allowing for ongoing learning among actors. Okay. Currently, in fact, the Ministry of the Environment has applied for one of these GEF grants and to push some of these ideas forward, and we're developing case studies with chefs to also look for opportunities in terms of other market streams for these biodiversity related seafood that could emerge from a turf reserve system. So from artisanal fisheries, we feel we've been advancing quite strongly from this system that was a single species system to ecosystem service management to something that's, I feel, more than co-management, but to ongoing co-learning initiatives where we can actually generate some innovation. The other thing I wanted to talk to you about had to do with aquaculture. In aquaculture, I'm going to focus mainly on ocean acidification. So if you just look at the research on ocean acidification, the socioeconomics impact approach has focused mainly on the direct impacts on humans through declining production, effects on growth rates, revenues. So what's usually done is you assess the ecological impacts, sort of value these impacts, and you project economic losses. That's what's being usually done. And with those type of analysis, studies have calculated that, I don't know, could be a reduction in 6 to 25% in the next 50 years in US mollusk fisheries. By the year 2100, annual global economic costs on shell fisheries could be between 6 and 100 billion, depending on demand and future demand. Even in Chile, we've estimated the impacts of ocean acidification over the growth of mussels in reductions between 13 and 28% of production. All these studies that follow this type of an approach recommend the need to understand how markets, companies, and local communities will respond to changes associated to ocean acidification, more than only analyzing a value in decreased production or decreased revenue. Okay, so much of the work we've been doing, and it's an important industry in Chile, has to do with mussels. Mussel aquaculture in Chile, it's a very important sector, around 280,000 tons, more than 600 companies. It's very interesting from social point of view as well, because it's a very heterogeneous sector. I don't know, you have anything from companies that have 13 long lines to 8,000 tons of production. There's no hatchery. Along the supply chain, you've got different actors. You've got artisanal fishermen sometimes in the beginning of the supply chain, and you've got companies across different sectors. So when we go into the effects of ocean acidification over market attributes and human well-being, in order to understand and link social preferences to ocean acidification impacts, the first thing we have to do is to try to experimentally assess the impacts of ocean acidification over commercially relevant physical and nutritional attributes of mussels. A lot of the research had been done on ocean acidification impacts over larvae, over juveniles, but very little over the commercial attributes of these organisms. So when you do that, and I don't want to go into details here, but you can see that there's a loss due to ocean acidification due in the color, fatty acids, proteins, the vitamin B12. These are some commercial attributes, okay? The strength of the shell also, I missed there, that are impacted by ocean acidification, okay? So with these, knowing how these attributes are impacted, what we did here was a choice experiment to try to assess the marginal effects of ocean acidification to consumers, okay? So consumers could decide under different options what they wanted to buy. The main results show that the attributes affected by ocean acidification are important to consumers, presented more than just those attributes, but these were important to consumers, that in fact consumers would be willing to pay in average 52% less for mussels with signs of ocean acidification than for mussels without those signs of ocean acidification, and that actually they're willing to pay more in their current price to mussels to avoid the negative changes in these attributes. Okay, so these are attributes that are commercially very important to consumers. What is interesting also has to do with recent research just published about how within the production system there could be some environmental refuges, for to avoid some of these negative changes. So this recently published study did control and transplant experiments, 1 meter depth, 4 meter depth, where these mussels are cultivated, and you can see how the performance when they're at 4 meters is greater than at 1 meter. Okay, so there's potential again to start co-learning with the industry and co-developing maybe innovation. Let's see what happens. They're niche innovations. They could go positive. Maybe we realize that they're not going to work, but at least we're trying together to innovate in terms of seeing how to avoid some of the negative changes in some of these attributes. In essence, through understanding the impacts of ocean acidification over marginal changes in mussel attributes, we're linking global phenomena to consumers at local scales. I think that's pretty interesting. And this also leads us to start incentivizing novel co-production and niche innovations that could emerge. Okay, so again, we're really going from an analysis to like a co-construction of ways forward for some of the sustainability problems we have in the Anthropocene. My final point has to do with research we've done on adaptive capacity of the mussel industry. And here we've, of course, assessed past adaptive responses. We've done scenarios to assess future adaptive responses. We understood the differences between adaptive responses that target productivity or that target price. And what I feel is pretty interesting, we're trying to do science to understand how we can finance science to develop early warning systems. Chile will never have the money to monitor all the interior sea, everything we need for climate change. So we have to start designing innovative systems to finance all this climate change science that could be applied to the industry. And here what we found out, we found out how different characteristics of the industries, so large industries, those that already invest in collective action, who have responded to crises by previous crises by extending production cycles, are more willing to invest in these early warning systems. So in essence, what we've been doing here is we're trying to first understand how different actors have different tolerances and expectations about environmental risks. And the challenge now is how we can co-design with this information a system to finance the science of adaptation. Is it going to be a derivative type of system, profit sharing system? And this is again where we have to start co-constructing with the associations of mussel producers, how this could work. And again, how we can measure the possible scaling, the scalability of a program that could start co-financing these types of things. So in essence, if you ask me, from Chile, we've been doing social ecological research, we integrate, we sometimes separately, other times more linked, but around sustainability, the Anthropocene is here. We have to work to advance towards sustainability in the Anthropocene, and this requires us as researchers to engage with the responsibility of shifting lessons to action. This will require on-the-ground engagement. It is requiring on-the-ground engagement, place-based research with diverse partners. If you ask me, those are the broader lessons. It's not co-management, it's how do we actually engage with the diverse partners through learning platforms. I like calling them, other people call them these niche innovations. We can create different ways, different arenas to co-produce knowledge, to co-construct different governance arrangements we might need. I know it might be hard, but in my opinion, that is the way forward. This is the way we have to go forward. This is the way we have to start advocating for sustainability through integrated knowledge systems. Thank you very much.
Thank you very much, Stefan. Interesting presentation. It certainly draws on many of the concepts that Dr. Berkes has already explained. You are trying to bring them down and to ground them on empirical data. We have a couple of interesting questions for you. You have talked a lot about collaboration, co-production of knowledge, and as we know from a very early paper, we need at least two to tango. It's not only it's necessary but not sufficient to have an eager community willing to participate in governance schemes and in sustainable management of resources. So the question by Jan Simon is, many states with collaboration, what are the best strategies to encourage state involvement in mutual learning processes through collaborative governance?
If only we knew, no? Like, yeah, there is, I guess, let me just frame this a little bit better, but I guess there's always going to be people in states as well, in state institutions. They're people, no? Also behind all these institutions. And some people are more prone for innovation, others are less prone. What I feel is interesting is how we can sort of start preparing for shifts or for developing niche innovations or for developing a learning platform that can then find a window of opportunity in order to get mainstreamed. So in my opinion, what we have done anyway, and I think it's working a little bit, is just providing these examples that things can be done differently. Sometimes that is easier said than done, because once these examples start gaining a little bit of traction, there's always going to be people that want to work against it. There's always people that like the status quo, because it's part of, I guess, some of these institutions' nature. But once you have a bit of traction with these learning platforms or these collaborative experiments that sometimes could be without all the actors, some element of the state can be interested, can engage, and can start generating a window of opportunity. Just to ground this a bit more specifically, some of the experiments we've been doing with fishermen establishing marine protected areas was very niche in a way, and just started with us. But as Chile has been transitioning and trying to approve a policy to create a biodiversity service, this is now becoming of interest to the Ministry of the Environment, not to the Fisheries Ministry or Undersecretary, but to the Environment Ministry. And now they're being proactive partners in this and helping sort of navigate and test this possible innovation with the other ministries. So you start getting these new things. So I just feel that we have to be patient. We just don't have to like sit there and wait for things to happen. But I think time and patience in terms of generating these collaborative engagements is very important. And sometimes we can be in a fast track, and then it all sleeps for 4 years, and then it comes back again. I just feel this is this is a posta. I don't know how you say that in English, but like a relay race. So we have to push all this together for years and years. This is not over in the next 4 years, 5 years, or 10 years. That's my personal opinion.
Thank you very much, and good that you use the word patience, because that brings me to the next question, and based on the introduction to the seminar and to Pablo Marquet's presentation, in the case of our coastal zone here in Los Lagos, probably there's not enough time. So Adrien Chevalier is asking the following, and I know you have also studied transformations in social ecological systems. So the question is the following: how do we know when a social ecological system will transform or is indeed already transforming and no more adapting to the current perturbations?
Okay, just before I answer that, I just want to say that when I say patience, I don't mean there isn't an urgency. Okay, just to be clear with that. I don't feel that we can just wait forever, but we have to do our work. But we need these cycles of learning, of trust, etc. Now, to answer the other question, we have a saying in Chile, and I'm just going to say it in Spanish, but todos somos generales después de la guerra. No, that we're all like generals after the war, because when we look back, we can sort of assess what a transformation was pretty well. I feel it's very hard to anticipate the transformation because it depends on so many different elements. I think what we can do is try to generate enough of these, I don't know, niche innovations, alternative ways of viewing, alternative narratives, collaborative arenas, deliberative methods for participation or whatever, so that when we're faced with an opportunity for transformation, we can sort of embrace it and shift in a more sustainable trajectory. I feel that just trying to envision one in the future is very hard, but again, that's me. Maybe there's other people who are better at envisioning those types of shifts. I just feel it's always easier to look back. But when we look back, we do have lessons, and these lessons, I think, have to do with the need to be prepared for a transformation. And that's where I think a lot of our research comes from, research like the one Fikret showed on social ecological systems, but a little bit more now going towards co-production of knowledge, developing platforms that could be multi-scale, etc., could eventually be useful. We just don't have to get upset if some of these fails. Failing is also part of advancing, and that's. I'm not very good at answering questions, but yeah.
Great. We have time for the last one. It's also by Adrien, and let me rephrase the question. If you were able to participate in the writing of our new constitution in Chile, what would you like to write down in stone in order to push towards the optimistic transition we are looking forward, thinking on the fishing and the aquaculture sector in Chile?
If I get to write, I think I'll just get 2 words in. That would be in reality. And if I get 2 words, I would probably go for environmental justice. I think those are the words we need to get in there. Of course, we all want the environment, etc. But my 2 words, when I get half a second, I would push that the concept of environmental justice within the Constitution.
Thank you very much, Stefan and Dr. Berkes, again, for this interesting chapter of our seminar. Thank you very much again. Following the same rationale, we will now dive into the Chilean aquaculture seas. And for that, we have Dr. Alejandro Buschmann from from home, from Universidad de los Lagos in Chile, and he will present his vision about the industry and its development in recent decades. Welcome, Dr. Buschmann.
Good afternoon. My name is Alejandro Buschmann. I'm full professor at Universidad de los Lagos. I'm part of the research team of Centro y Mar in Puerto Montt, Chile, and also part of the Center of Biotechnology and Bioengineering in Chile. So I will talk today about the interaction of aquaculture and environment, and how the development of aquaculture in southern Chile means that we need to take care about different environmental aspects to make this activity more sustainable. Okay, Dr. Ross Naylor just presented us a very good general view of what happens with aquaculture in comparisons with the fisheries. Fisheries have reached a plateau during the past 10 years, 20 years, and aquaculture is taking a major part of the increment of seafood available for humanity. So this is happening. This production is becoming more and more important. And in Chile, this is happening also, perhaps at a lower rate, but in green are fishery landings, and you have seen that 2014 we had some of the highest landings that during the last 2 years, but after that, 2015, 2016, 2017, we have seen a decline in fishing. But in blue, aquaculture, and in Chile is mostly marine aquaculture, has been growing steadily during the past 20 years. In 2000, we had a production of roughly 400,000 tons. Right now, we reached about 1,200,000 tons, which means threefold increment of aquaculture landings in the past 18 years. Another point that needs to be taken about aquaculture development is that here we have during the past 30 years the increments of human population. This is a log scale, so you don't see the exponential growth of the human populations and this linear growth. We can see that milk and cattle production is under the population growth curve, meaning that this is less and less meaningful for human availability as food. But pig production, eggs, chicken are increasing their production. But aquaculture is increasing much faster. But we need to understand what aquaculture production means. And here we can see that most of the production is freshwater finfish. So freshwater aquaculture of organisms like carps, tilapia, is the most largely the source of aquaculture food coming to becoming available to humans. Bivalves is the other item, much less crustacean, shrimps, and marine fishes and other organisms. Is a small amount of the production, aquaculture production system. From Chilean perspective, we think marine fish is the most valuable ones, maybe from an economic point of view, but from a food source supply to humans is not a large quantity of biomass that becomes available. In Chile, as I said, Atlantic salmon is the most predominant, Pacific salmon and trouts also. There is mussels, 3 species, but mostly one, Mytilus chilensis, the red abalone, the green abalone, scallops, Gracilaria, now called Agarophyton, and some microalgae are the major species production in Chile right now. So mussels are increasing during the last years at a slower rate, but still we have some increments. Salmon has been increasing during the last year, and after the last losses due to Isa virus crisis, the growth started again, and right now we are reaching around 800,000 tons per year. So seaweed, they were important in the past. We produced it during the early 90s over 100,000 tons per year of agar, of Gracilaria for agar. Right now it's a small amount, and this is maybe due to economics. The number of licenses, well, most important for fish, then for mollusks, macroalgae, and this means that we have over 33,000 hectares of licensed areas for aquaculture in Chile. That was a rough, brief overview on aquaculture development in Chile. Now I will introduce the environmental part. I will use, for starting, a recent definition raised by Buschmann and collaborators in a book called World Seas and Environmental Evaluation, in which she defines near field and far field environmental effects. Meaning by near field, those environmental effects that occurs or take place nearby in the same culture site and within tens of meters. And far field are those impacts, they go beyond the salmon or the aquaculture facility and affect a larger surface of the coast. So at least several hundreds of meters or kilometers away from the culture site. Typically for Buschmann, benthic effects, organic enrichment, water quality, reduced oxygen, altered nutrient dynamics, release of chemicals, and habitat modification are typically near-field ecological effects. Far-field ecological effects for these authors is the spread of diseases and pathogens, introduction of invasive species, altered food webs, marine litter, mostly today we are talking about plastics, microplastics, and so on, are far-field ecological effects. These effects impact in a much larger scale. As I will introduce, I will show that some water quality impacts can be far-field, and I will make a point for that. Okay, let's have a fed aquaculture. Finfish, normally what we talk is finfish production in Chile salmon farming. We introduce feed with nitrogen, phosphorus, carbon included, no? Most of the this component, they go and reach the sediment, and about 65% of the phosphorus coming from the feed enters the system. And only 23-25% is taken out when the fish is harvested. Everything else remains in the environment. And nitrogen, from 100% of nitrogen, only 15% goes in the bottom, but most of the nitrogen comes out as dissolved inorganic nitrogen, ammonia, into the water column in the photic zone. So it's nitrogen available for primary producers. So macroalgae, microalgae can take that nitrogen. And this, I will make a point, that can go far away from the culture side. On the other hand, there is biological pollution, escapees, the pathogen spread, parasite moving out of the cages, invading native fishes, for example, and that affects all other kind of organisms that are related to this organism through the food web. But in addition of that, there is some chemical use, like antibiotics, that also move out of the cages. And I will make the case that this can go further at a longer distance than just being nearby the salmon farm. So I will talk in the next, during the next time about nitrogen loads to finfish production and antibiotics entering the system. And I will start with antibiotics. Well, why the problem of antibiotics is mostly that we expect that by year 2050, infectious diseases will be the cause of death of human beings, the major cause, even higher than cancer, which is today the reason why people died, mostly died at the present time. So there are several reports about this. Almost everyone agreed that this is a tendency, and we need to control antibiotic use by humans, but also in animal production. So what happens? In aquaculture sites, biodiversity of bacteria have a tendency to be lower than in control sites, but also the composition of bacteria is modified. The community structure of the bacterial communities in the sediments is modified due to aquaculture. On top of that, we have antibiotic use. And during the 90s and 80s, Norway was using quite large quantities of antibiotics, but through innovation process, they have reduced antibiotic use, but still Chile is its production, salmon production, is highly dependent on antibiotic use. We have made some improvement in the past years, but still we are a heavy user and there's a lot of room for improvement. One important point. Here we have the antibiotic resistant fraction of the cultivated bacteria, And we can say that in the culture sites, which is zero distance from aquaculture site, For oxytetracycline, oxalinic acid, and fluorphenicol, we have a high percent of bacteria, antibiotic-resistant bacteria. This has a higher frequency of antimicrobial genes that they confer this property to the bacteria. We have demonstrated that. And this high resistance stays in the system without a significant reduction, at least 1 kilometer away of the culture system. In a control that is 8 kilometers away, we have a reduction, significant reduction. But still, we don't know how much it is reduced in between. So I can only say at least at 1 kilometer, we have still an effect of the culture, the cultivation of salmon on the resistance of bacteria. In addition, I am willing to mention that sediment analysis as far as 8 kilometers away, we still can find traces of antibiotics. So antibiotics are moving much more than we think, and following the definition of Weizmann, this should be a far-field effect. In addition to that, antibiotic use can be found in wild fishes that are swimming and eating surrounding their cages, and they eat medicated pellets, and antibiotics can get into the flesh, fish flesh. So people that are fishing, collecting this fish, bringing to their tables, eating it, they will have a doses of antibiotics. Not a very high doses, but antibiotics will be in their diet. And by analyzing the frequency of genes that are present in a uropathogenic E. coli, we have found that in Puerto Montt Hospital, patients that are coming from coastal zones where aquaculture exists, they have a very high frequency of genes that provides antibiotic resistance to these pathogenic bacteria. And this is much higher if we compare it to a US hospital where patients with the same, for this same pathogen, which has a much lower frequency of genes. So let's go to nitrogen excretion in finfish. We provide feed to salmon. Some of them are they are assimilated. The fish respire, produce CO2. We get defecation, feces. Some of them are going down. There could be some resuspension system process. But as I told you earlier, most of the nitrogen gets excreted through the gills by the salmon, and inorganic nitrogen enters directly into the water column, do not go to the bottom underneath the culture cages. By doing that, Olsen and Olsen provided some estimation how much, for example, 800 tons of salmon produced in Chile, how much nitrogen can be coming into the ecosystems, coastal ecosystems in southern Chile. Remember, this is the production, more or less the production during the past years. So the number here, a magic number is that over 22,000 tons of ammonia can come into the environment. And this is quite large. The total nitrogen loading is over 24,000 tons. So this is more or less equivalent from a population of 11, 12 million people. All the excretion by a population as that is large enters directly into the water of our coastal systems in southern Chile. Has this a biological meaning? Here was the first experiments done in mid-90s by Max Troel doing his part of his PhD thesis. We put Gracilaria near a salmon farm, 100 meters away, 500 meters away, in February, summer, not limitation by light, high temperature, good temperatures for growing Gracilaria, and at different depths. So we can see that with depths there is a loss in the growth rates of the response on growth of Gracilaria because of light limitations. But in any case, the growth near the salmon farm was significantly higher than if we move the culture of this seaweed farther away. We repeated this experiment and the same conclusion was arrived. During summer, during the limit when no nitrogen is naturally low, the inputs of salmon can determine a enhanced growth response of Gracilaria. And even more, the nitrogen in the tissues can increase. And this is a proof that they're using that nitrogen if they're nearby the salmon farm. And they also increase then the amount of phosphorus in the tissues. So the nutrients coming out, inorganic nutrients coming out and staying in the water column can be used by primary producers. Okay, this experiment was done in a case with a small salmon farm that produced only 400 tons per year. But we repeated this experiment later with Dr. Abreu from Portugal, also doing his PhD thesis in Chile. And she did these experiments, but now in a place where we have a large-scale commercial size salmon farm, producing over 1,500 tons. So at least three times larger as in the previous example. And the results is quite the same. We have an increased growth rates, increased nitrogen in the tissues, but now as far as 1 kilometer away from the salmon farm. So by increasing the scale, the impact of aquaculture gets larger, and phototrophic organisms can sense the increment of nitrogen as far as, I can say, at least 1 kilometer. And just by difference of the surface volume ratios between macroalgae and microalgae, that makes me thinking that for these unicellular organisms that can uptake much easier the nitrogen because they have a lower volume surface ratio, they can also be very efficient taking up this nitrogen and producing blooms of microalgae. In addition to that evidence, we have shown that the levels of the isotopic nitrogen values is increased for a brown algae, a red algae, and a green algae in the fall when still we have a low levels of naturally nitrogen in the water, and we have an increment of this higher value nitrogen, isotopic nitrogen, meaning that this nitrogen is coming from the salmon and not other source. For lowering these impacts, there is the case of IMTA, that this idea that has been developed, some work done in the US in Florida by Ryder and co-workers. And the idea is that near fed aquaculture, mostly finfish, we can have organic shellfish that take up small particles. The larger particles can be extracted by invertebrate that can eat the organic material that comes into the bottom, and then the inorganic fraction can be taken by seaweed. The main problem for demonstrating that is that we need a full-scale, large-scale experiments. I cannot have few algae to demonstrate that I can lower the concentration of nitrogen in a whole bay. But in China, they have these systems, and they have very large-scale Gracilaria productions. And when we have this case, they have demonstrated that nitrogen levels, which is the limiting factors, can be lowered, and then the amount of phytoplankton, the phytoplankton density, is significantly reduced. And even more, we have a reduction in toxic microalgae blooms. The frequency of these blooms has been reduced. So this evidence indicates that we can do things, and we have an avenue to explore, but we need to do large-scale experimentation. So antibiotic and nitrogen loads data indicates their impacts reach beyond the aquaculture site limits. So the impact of this salmon facility goes much farther from the locations and where regulations requires to be sampled for testing environmental impacts. These effects are more diluted, are not as easily to work with, but also if you have other aquaculture activities, it will start to interact with these other aquaculture activities, making much more complex the problem and finding the result, the right and correct interpretation of the results. So, having presented these results, I can say that we need to modify regulation systems, increase the environmental response at a larger scale, internalize economic impacts, producing quotas, production quotas, depending on waste inputs, for example, can be others, and limitation of the use of some products, like antibiotics and other products, in our regulations. We need to move into more strict regulations. In addition to that, we need to develop an environmental monitoring program with open access and validated data that support analysis, deeper analysis, and better and come to better conclusions about the quality of our environments in southern Chile, in North Patagonia. Third, I think we need to enhance the research capacities in Chile to produce better information towards a more sustainable aquaculture system in the country. Introduce perhaps IMTA or other bioremediation strategies into the systems and become much more resilient that will take place due to climate and oceanographic uncertainties that are coming to every coastal areas in the world. And in the Patagonia, things are happening already. And Dr. René Garreaud will talk more about that. So these are the main conclusions. Thank you very much and enjoy this workshop.
Thank you very much, Dr. Buschmann. We are a bit late, but we still have time for a couple of questions posed by the audience to you. The first one is the following. The talk has highlighted many impacts, and it is clear things must be improved. But how do the environmental impact dimensions compare to food production impacts on the land? What are, in your opinion, the trade-offs between producing food on land versus in the ocean?
Okay, the main difference is that in the water you are in a continuous flux of water. In terrestrial systems, your waste mostly are coming to the soil, filtered, and then enter to the water. So it's a passing through the soil first, and during that you can do some management of your waste. And the solid wastes can be separated much easier. In the case of aquaculture, the solid waste that goes down under the cages, it's quite complex for say, to take it out of the ecosystem. I cannot easily pump that out, and what can I do with that is also complicated. It's not easy to manage. There has been some ideas to bring it to field terrestrial fields of corn or whatever, and throw it, but you're bringing also a lot of salts. So salinity changes can be quite important. So it's quite a different system, how you can manage, what you can do. I will say, with the actual knowledge, it's much more complex to manage the waste in the sea or in the water than what the terrestrial farmer now can do with his manure in his field. So I think that is the largest difference.
Okay, thank you. So we can interpret you are a promoter of producing, increasing the production of seafood on the land. But
I will not say that. I will say we need to have systems. I think aquaculture has something to do. And as demonstrated earlier, in the talk by Ross, aquaculture is becoming important. But the point is how we can do this industry more sustainable.
Yeah,
that we need to move forward on that.
Exactly.
And there are several avenues that we need to think about and demonstrate how we can do it much better than what we are doing it now.
Exactly. The next question refers exactly to that. Since we still have a huge aquaculture industry in Chile, including salmon, mussel, and somehow also seaweed, how can we understand that the IMTA has not so far worked in Chile. And you have mentioned that in one of your last slides.
Yes, it has not only has not worked in any place, I will say, in a commercial scale. And that is mostly because of economics also. If you go to a salmon farmers and that have making some millions of dollars per year, and I will say, well, you can introduce 1,000 hectares of seaweed and do it and make maybe $500,000 with a very large input of effort and work for doing it. They will say, I don't get the same compensation for my effort, no? So what we can do with seaweed, normally in the Western world, we are not eating the seaweed. The seaweed can have a high value in Oriental countries where they pay for as a food item. But we are selling it for chemicals like a commodity. So we are shipping seaweed to China, Europe, and well, some products are processed in Chile. But for example, in brown algae, we are exporting most of that. And that is not, we're not making a lot of money. We cannot pay with that revenue the aquaculture development. So we have to learn what to do with that biomass, how we can process it better, how we can just think. Today, the polysaccharide industry, they use 30% of the biomass and 70% of the rest is residue, waste. So it's not an efficient use of that biomass from at least my perspective. So we had a lot to do for increasing the value of seaweeds to being used as a biofilter and then create a demand for that biomass.
Thank you very much, Dr. Buschmann and Dr. Naylor, for your interesting presentations. I'm obsessed with the lack of applauses in this virtual format, and this is not only for the speakers, this is also for the audience, because we are heading into the last section of our seminar, and it's time to hear Dr. Catriona Hurd from the University of Tasmania in Australia. Please, Dr. Hurd, your presentation.
Hi everyone, it's Catriona Hurd here, just coming to you from my attic. I've been working at home for a while now. So hopefully I'll see you virtually tomorrow, and I'm going to talk to you now about climate change and seaweed primary production. So I'm just starting my stopwatch. This is the 5th time I've tried this now, and I keep going over time, so I'm hoping I'll be under time this time. Anyway, this is my title. And I'll talk about seaweeds and just their diversity and role in coastal systems, and then I'll talk briefly about rain shifts that we're seeing. There are multiple drivers of environmental change, so this is a recent research field. It's evolving quite rapidly. I'm going to talk about a couple of single drivers, temperature and ocean acidification, and how we study those, and then multiple driver experiments as predictive experiments for predicting how seaweed might respond in the future. And I've got a couple of examples that I'll give you there, Macrocystis and Philosphora, both brown seaweeds in this case. So just start off by talking about seaweeds. So there's about 11,500 globally species, and that's probably a massive underestimate because there's a lot of cryptic diversity that we don't know about. And they come in three colours. One's the red seaweed, and there's about 7,000 species. They're the most ancient group, about 1.2 billion years old, and they are related to terrestrial plants because at the moment anyway they're in the kingdom Plantae. That has changed over the years. And they come in fleshy forms like that one I just showed you, but they also have these what we call calcifying forms. And these are seaweeds that impregnate their surface with cell walls with calcium carbonate, and they're actually very important ecologically, and they're very sensitive to ocean acidification. I'm not talking about them much more than that. And then green seaweeds, 1,500 species, and these are about 54 million years old, and they're in the kingdom Plantae. So these are the ones that are quite closely related to terrestrial plants, relatively. And then we have the brown seaweeds. Here's Davilia potatorum, the Australian Davilia species, and they're about 24 million years old, about 2,000 species. So these are relatively young, recently evolved, and they're in a different kingdom altogether. They're in the Ochrophyta, so they're not. So my point here is that these are three groups of seaweeds that are not closely related at all. And so if we're trying to predict how seaweeds biodiversity or might change in the future, results of experiments we do for brown seaweeds are likely to have little relevance to those for red seaweeds or green seaweeds because they're so physiologically and evolutionarily different. So why do we study seaweeds? This is for people who don't spend their days thinking about seaweeds, which is all I do. They're responsible for 50% of primary production in coastal systems. So half of the carbon fixed in coastal systems is by seaweeds. The other half, of course, is from phytoplankton. But they create habitat and shelter for fish and invertebrates. So if the seaweeds weren't there, there would be no habitat. They're ecosystem engineers. In Australia, they support, this is a tourism and fisheries industry, aquaculture of 11 billion per annum. That's the ecosystem goods and services that seaweeds provide, that number. There's not really an industry for seaweeds in Australia, but globally there's a massive industry for seaweeds, for food, pharmaceuticals and so forth. And that's worth about 6 billion per annum. So these seaweed communities are on the move. They're shifting. Northern hemisphere species are moving northwards towards the Arctic. And so in the southern hemisphere, there's a bit of a problem for countries because there's actually nowhere for the seaweeds to go. There's no land mass that they can get to because the Antarctic is cut off by the circumpolar current, and hopefully that will stay like that. So our seaweeds in the southern hemisphere don't have the same ability to migrate south as the northern hemisphere species have to migrate north. This is because I'm doing it for the 6th time. I'm losing my voice. So kelp forests are in global decline. There's a lot of evidence around that. And marine heat waves is perhaps the most recent stressor that we've added onto our list that affects seaweeds. So multiple drivers of change. So there's a lot of things changing quite rapidly at the moment, very rapidly. Temperature's increasing, as we're aware. We know that carbon dioxide is increasing in the atmosphere, and when that dissolves into the ocean, it causes carbon dioxide in the ocean to increase, but also the pH of the ocean to decrease. That's why it's called ocean acidification. Nutrient supply is being altered. That's because the stratification of the surface layer is changed, and there's going to be stronger stratification, so nutrient supply, so nitrogen, phosphorus will decrease. We have salinity is problematic, particularly in the poles where we've got ice melt. That is a major driver in some systems, estuarine systems too. And deoxygenation of the seawater, which has rarely, has only been studied with seaweeds once, but it almost certainly will have an effect. And then we've got, on top of these global changes, these ocean global change drivers, we've got local change in coastal systems. So we've got eutrophication here, we've got pollution, runoff, sediment, and so forth. So this is all happening simultaneously. And the question is, how do we study that? I'm starting off the next slide. I'm just going to talk about temperature and how we can study temperature effects. Then I'll move on to ocean acidification. Oh, actually, that's not entirely true. I've got this slide first. So predicting responses to multiple drivers, most studies have been on one climate driver, and the most common climate drivers so far are ocean acidification and temperature. They're the popular ones. Some studies have looked at 2 or 3 drivers, and there's some good studies on this out there. However, once you get more than 2 drivers, traditional factorial designs are almost impossible to interpret correctly. So we need some more designs, and I'll talk through a couple in a minute. And then studies on natural systems, for example, the effects of a heat wave or the effect or ocean acidification along a volcanic vent. These are incredibly useful as well. However, they are usually just focusing on one driver as well in OA or temperature extremes. So temperature, approaches to looking at temperature, the experimental approaches. Temperature's probably the ultimate driver because it affects every single rate process and every seaweed, and it sets biogeographic boundaries. And the thermal response curves, these are incredibly useful for predicting species ranges. So this is an example from Thomas Wernberg for 3 Australian brown seaweeds. And you can see each species has got a different thermal optimum and a different range of temperatures at which it grows. And this corresponds very well to their geographic ranges. These sorts of experiments can be really useful for acclimation studies. So you can grow seaweeds from juveniles under different temperatures and see if the thermal tolerance changes. And there's surprisingly few thermal response curves for seaweeds. And I suspect this is because in the old days, certainly when I started doing work on this, temperature really wasn't considered to be important in seawater because it's quite stable in seawater compared to in the air. So anyway, surprisingly little work on this, and certainly a lot of room for some studies on this. I've got one later that I'll show you. Ocean acidification is very complex to study, and itself is a multiple driver. When we started working on ocean acidification, it all seemed horribly simple, you know. Basically, pH was going down, anything that calcified was going to dissolve, everything else would benefit because there's more carbon dioxide in the water. It's just really not that simple. And so we've got, it's a multiple driver because protons are increasing, so the amount of hydrogen ions in seawater increases, and that's obviously what causes the pH to decline. But remembering that hydrogen protons are actually biologically important, incredibly so. Dissolved carbon dioxide is increasing, that will increase by 200% by the end of this century, and bicarbonate's also increasing, and both of these are used in photosynthesis, and that's going to increase by 14%. And then we've got the saturation state of calcium carbonate is decreasing. So this is the parameter that determines whether things dissolve or not. So calcifying organisms, so that's all the marine calcifiers, including coralline seaweeds, are affected by this parameter. So calcifying seaweeds mostly respond negatively to ocean acidification, but fleshy seaweeds, we really have not got much of an idea how they'll respond still. And we did a survey here, of a literature survey, which we found 60 species that have been studied, and not all of these are ocean acidification experiments. Some of these are CO2 addition experiments, which is a bit different. But anyway, 24 species had no response, 18 had increased growth, 5 had decreased growth, and of course, as always, the same species in different studies responded differently. So at the moment, with fleshy seaweeds, there's no obvious patterns in terms of either phylum, as in red, greens, browns, or orders within those phyla, or their physiology. So we haven't figured this out yet. This is ongoing work in my lab, and I know in other people's labs too, because it's important stuff. So, multiple driver experiments. How do we do these experiments? I've already said that as soon as we get past 2 drivers, experiments become incredibly difficult. We know we've got 5 drivers changing simultaneously or more. It depends on the system. Different drivers are important in different systems to different extents. But let's say we want to do an experiment with like 3 drivers even, it becomes really difficult to analyze the data and some of the, and the factorial design doesn't actually work that well. So we need more different experimental approaches. Now, luckily, of course, there's been this SCORE working group, 149, changing ocean biological systems. So this is an international team, and you can see Jorge Navarro here from Chile. There's myself, Philip Boyd's the leader. We've got Kunshan Gao from China, Dave Hutchins from the States, Christina McGraw from New Zealand. And the task of this working group was to come up with new experimental designs for studying multiple stressors or multiple drivers. There's a lot of discussion as to whether we call them stressors or drivers, but we went with drivers in the end. And so this group came up with a best practice guide. This is available online. It's free. You just go to the SCORE website for Working Group 149 and you can download it. The groups also run a bunch of training workshops, and I was actually supposed to be at one right now in Peru at the High CO2 World Conference, but obviously that was cancelled. But never mind, there will be more in the future. And these are to help students and any researchers actually learn how to design these multiple driver experiments. So I'm just going to give you a couple of examples, I think, from my research in my lab. And the first one's on Macrocystis pyrifera, and you'll know the person who's done this work, or all of you in Chile at least should know who she is. The photograph here was taken by Joanna Smart, an honour student of mine. I just think it's fabulous. And here's a Macrocystis bed in the background. I'm assuming that's not in Tasmania, and I'll show you why. Because in Tasmania, we've actually lost 95% of a Macrocystis bed since about 1940. And the reason for that is that the current systems, the warm current systems, have migrated south. So whilst we used to have cold water flowing on the east coast, we've now got warm water flowing down the east coast. And so Tasmania has actually warmed at 4 times the global average, and the result has been a 95% decrease in Macrocystis beds on the east coast of Tasmania. Here is Tasmania, here's the east coast. So this is Pamela Fernandez, and who led this research, and the second part of the research was undertaken by Matthias Schmidt. So when I arrived in Tasmania, there was all this, people kept saying to me, oh, there's loads of Macrocystis where there's nitrogen enrichment, for example, in sewer outfalls. So there's still patches of Macrocystis. And this is observational evidence. It hasn't been properly documented. And in terrestrial systems, it's well known that when you give terrestrial plants nitrogen, it can actually increase the thermal tolerance, because nitrogen is a limiting nutrient, and it's limiting for seaweeds and also for terrestrial plants. So Pamela's question was, could increasing nitrogen supply to Macrocystis enhance its thermal tolerance? And if that's the case, what's the mechanism of enhanced tolerance? So obviously the answer is yes, because otherwise we wouldn't have gone on to the second part. But these are data from Pamela's paper. So nitrogen enrichment enhances thermal optimum for photosynthesis. So here's photosynthesis, here's temperature. We have nitrogen replete seaweeds. So these are seaweeds that are full of nitrogen. They've been grown in high nitrogen concentrations. Still at natural levels though, I must point out, naturally occurring in the field. And then we've got nitrogen deplete ones, so ones that have not, which are naturally nitrogen deplete. And you can see here that the temperature optimum for photosynthesis increases by 3 or 4 degrees when they're given nitrogen. So what this shows is that a local driver, which is nitrogen, can mitigate a global driver, which is temperature. And there's the mechanism here is that nitrogen deficiency reduces biochemical acclimation at high temperature. And if you just look at this graph, if you look to the right, the 3 bars on the right here, this is the high nitrogen or the nitrogen sufficient seaweeds. And on the y-axis there, you've got lipid class. So these are the different types of lipids in the cellular membranes. And there's no effect of temperature on the cellular membranes for the high nitrogen treatment. But when you go to the low nitrogen, so these are the nitrogen deplete or the nitrogen deficient seaweeds, as temperature increases, you get an increasing amount of sterols and free fatty acids. And what this means is the cellular membranes are actually degrading. They're breaking down. And so by increasing nitrogen, the seaweeds are able to maintain the cellular membrane. And so they're able to maintain photosynthesis better. And this has been found for terrestrial plants as well. Okay, so now I've got a second example here. This is Philospora camosa. So this is a habitat forming Fucales. It's only found in Australia. So this is a Fucalian seaweed. It's got a really wide temperature distribution. So it actually grows from, Australia is a massive country, not as long as Chile, but it does go all the way from the tropics, the Great Barrier Reef, right down to cold water, cool water. So this one grows from the north of Sydney here all the way down to southern Australia to the tip of Hobart, and actually around the entire southern part of the country. So it's endemic to Australia, and previous work suggests that it's sensitive to marine heat waves. So there's studies suggesting that when you increase temperature, this seaweed does badly. So we wanted to ask the question, how does it respond when you give it future conditions of ocean acidification, temperature, and a marine heat wave? So we've got three drivers in this experiment, and the take-home message is in the title. It's to do with fatty acids again, but I'll get to that in a moment. So this is one of these new experimental designs that we've used, and it's called a collapse factorial design, and it's design in which you reduce the number of factors, so we only have we can use three drivers. So it's not factorial. We're not testing OA, you know, 2 levels of OA with 2 levels of temperature and 2 levels of heat wave. You'll see the design in a second. And these are predictive experiments, so they allow us to test future scenarios against today. So what you lose, or you can lose in these experiments, is some of the underpinning mechanisms, although we actually did look into that. And this is the first time, to our knowledge, that this design has been used for seaweed, so collapse factorial. So this is what the experiment looks like. So Philospora juveniles, we've got 4 experimental treatments. So we've got today, which we've called current baseline, so today. Then we've got today with a heat wave, and this mimics the heat waves that we've seen in Tasmania here, an increase in 3 degrees over a 5-day period. And then we've got future. So this is future temperature, future ocean acidification, and future heat wave. Oh, here's future heat wave. So we've got future baseline. So this is only when you increase ocean acidification and temperature. And this is when you do the same and throw in a heat wave over 5 days as well, another 3 degrees increase in temperature. So what did the results look like? Well, they were great. There was actually no effect whatsoever. So hang on, let me just go back if I can. So we sampled at 2 times in this experiment. We have sampling day at the end of the heat wave, and we compare that to the end of what we call a recovery period. So they're basically acclimated here, and then they have a heat wave, and we measure here and here. So there's no effect at all on growth or photosynthesis. And here's relative growth rate, and here's photosynthesis. There were some effects after the heat wave, but those had disappeared a week later. So why is there no effect? Well, yes, once again, we looked at fatty acids. This is Matthias Schmidt who's doing this work. And why is it tolerant? It seems that once again, that cellular membranes become fluid at higher temperatures. We didn't see this response. And what we think is happening is that we've got increased CO2 supply. It appears to enhance the thermal tolerance. Now, the mechanism for this is different to the mechanism that I talked about with nitrogen, but it is to do with the seaweed having an increased supply of what can be a limiting resource, and therefore it enhances its thermal tolerance. So another example of how 2 factors that, so temperature, as I said, independently has been shown to be negative for this seaweed, but when you increase temperature and ocean acidification at the same time, we didn't get an effect. Okay, so to summarize, And this time I'm under time, but I think I'm going to live with the under time scenario rather than the overtime scenario. So I'll just summarize. Multiple drivers is a relatively new research field, and the experiments are difficult. They're difficult to do, and it's because seaweeds are large, and to replicate correctly, factorial designs just don't work very well. Sorry, I don't mean to diss anyone who's done factorial designs, but there are probably now methods that are can be an improvement. So there's still being methods are still being developed and tested, and I certainly advise you to, if you're interested in these sorts of experiments, to have a look at that website. Predicting how seaweed communities will respond to a future ocean is difficult, and so we need these new experimental designs, and we need mechanistic understanding if we're going to help make predictions. So we need to know the mechanisms by which red, greens and brown seaweeds are acclimating or can adapt to seaweeds, and across different parts of the life cycle too. Field studies at natural systems are really useful, but it's very difficult, if not impossible, to do these predictive experiments in a natural system, although obviously mesocosms can be used in the field. And then I said I'd talk about biodiversity briefly. Well, I am. So species, I think obviously they're going to change. The biodiversity of local systems will change. There'll be species contractions and expansions, as I showed in that Strauss paper. Wernberg's a co-author. And not only that, there's novel habitats being created right now. And a really good example is tropicalization of temperate reefs in Australia. So north of Sydney, a place called Coffs Harbour, we've actually, because it's warming, we've got this interaction now between tropical coral reefs. So coral reefs are migrating south, and they're actually moving into seaweed-based systems. And now you've got a new ecosystem that's got corals, which are not actually forming the habitat. They're part of the habitat along with seaweed. So you've kind of got two ecosystem engineers coexisting. That's completely new habitat, certainly for that area. And at the moment, our knowledge for the big seaweeds it's quite hard to predict winners and losers. And, you know, there's a whole bunch of stuff I haven't talked about, but you've got genetic adaptation, we've got acclimation, there's all these things. We've got people are trying to recolonize areas, habitat restoration. So there's a bunch of ways in which we humans can improve systems. But right at the moment, our knowledge, there's quite a few large knowledge gaps, I believe, that need filling to make better predictions for the future. And I'm going to finish it with there. And I am looking forward to seeing you all later. So I'll stop sharing. And now I'll...
Thank you very much, Dr. Hurd. I have two questions in one for you. And it reads as follows. Because sometimes it is hard to include multi-stressors in an experiment design, which ones do you think are the most relevant to use for predicting kelp responses to climate change? Which is the importance of local adaptation in predicting these responses?
Yeah, so which driver to choose, I think, depends on your system. So you have to, that school working group I was talking about, we recommend, and there's resources on that website, that you go to your local system and see what the key driver is. So in Australia, for example, its temperature is by far the most dominant driver, and marine heat waves. But Chile might be quite different because you have an upwelling system, and then naturally, so you actually naturally have, in some cases, low pH water coming up to the surface. So so you may have a different driver system. So, and the Arctic, for example, salinity, and the Baltic, salinity is actually the more important driver. So it's a matter of picking those drivers and trying to work out how it, and then using perhaps models to predict, that are predicting how drivers in your area are changing, and then trying to use those in experiments. So that's how we did that philosopher experiment I was telling you about. We used the model projections from coastal Tasmania to work out those key drivers. So yeah, I think that's how you have to do it. So temperature is probably the most important driver globally, but it may not be on your local system. I've forgotten the second part. Acclimation, adaptation. I think that's super important, and there's relatively little work on that. With seaweeds, there's some nice work, again, that I'm familiar with in Australia from Melinda Coleman. She's been doing work on eclonia and heat waves and genetic sort of diversity, and she's looking at adaptation at the moment. So those are probably the sorts of studies that need to be done. I'm not that familiar with the area, but also for coralline algae, again, Chris Cornwall's done some work showing that generations can adapt over a couple of years that was for pH, to a reduced pH. So I do think we need to look at that. There's not much about that at the moment, relatively. And it's because it's hard to do. Seaweeds are really difficult to grow through their life cycles in culture. So we have to do it with little ones.
Thank you very much for your response. Now I want to give the microphone to Dr. René Garreaud from the Universidad de Chile. I don't know if I've pronounced your surname correctly.
That's correct.
We look forward to hear your presentation on climate variability and change in Western Patagonia.
Last but not least.
Exactly. Thank you.
Hi, everybody. This is René Garreaud from the University of Chile, the Department of Geophysics and the Center for Climate and Resilience Research. And I'm really happy to participate in this virtual workshop. Actually, I would rather be there in Puerto Varas with you, but, well, this is not the case. Anyways, I am a climatologist, so I will talk today about a little bit about climate change and what has been going on for the last few decades, and also we will look a little bit into the future, what we should expect in the next 50 years. So in these 20-25 minutes, I have this little program here. I will start with some basic aspect of the climate in Patagonia, Patagonia 101. Then one important element is the relation between the precipitation and the zonal wind, the wind coming from west to east. We will talk about the climate variability and change. And I will talk about extreme events. When we look into the future, we tend to emphasize changes in the mean precipitation and mean temperature. But equally important, or perhaps more important, but more challenging, is the changes in the extreme events. And the year 2016 was a case of this. So we will take a little look on this issue of the extremes and how they impact the hydrobiological conditions in northwestern Patagonia. So this is the big picture in terms of the climate of the region. We are here in North Patagonia from about 40 degrees south. And this is a region where the mid-latitude westerlies and the associated storm track impugnates all year round. There is some seasonal variability in the position of the wind maxima, but generally this region receives the westerly winds from January to December during the whole year. And within this, you have baroclinic or weather system perturbations that are embedded in these westerly winds, and those are the main cause of the precipitation, of course, over Patagonia. In general, we like and we place a lot of attention. This is a particular day in which you can see a well-defined center of low pressure, what we call mid-latitude depression, and also disorganized the warm here, the warm front and the cold front, and the ones are those that deliver precipitation here in Patagonia. In this case, all the way from south of Chile to probably the southern part of the Aysén region. Most recently, we have been focusing in what we call zonal atmospheric rivers. Atmospheric rivers are long filaments of moisture, are corridors of moisture transport. You can see here, this is an image in which the yellow indicates the maximum amount of what we call precipitable water. And you see that in this particular case, this transport is oriented from east to west, or from west to east. Actually, it's impinging upon the Ausolandes. This is the satellite images. And these are the cases that actually produce the most of the precipitation in Patagonia, these zonal structures of zonal filaments of water vapor impinging against the Ausolandes. This particular case was May 1st of 2019, 19, and that's caused a significant precipitation. For instance, this is Estación Río Puelo, and it produced roughly 300 millimeters in 2.5 days. And one important event or a feature of this event is that they occur or tend to occur with relatively warm temperatures. These are the time, this is the precipitation intensity, and this is the temperature. So in contrast to a normal front, this particular case produced actually an increase in temperature. So this combination of high temperatures with a lot of rain reaching up to the top of the mountains and very strong precipitation rates. Here you can see some moments in which you have more than 10 millimeters per hour, even 15 millimeters per hour, rapidly translate in a flooding of the river, in this particular case, the Rio Puelo, and later in landslide and other kind of effects. Some of these events can be very dramatic in terms of their impact. Anyway, even if you have a traditional cold front or this new, I said new because we haven't worked on that before. It's not because they're new in the sense that they didn't exist before. New in the sense that we have a new look in this storm. Anyway, the point is that this frontal system embedded in the westerly wind belts produce this copious amount of precipitation that is about, let's say, 2,000 to 3,000 millimeters per year in the coastal areas, and that's increased rapidly because you have the Austral Andes. The Austral Andes are not as tall as the subtropical Andes, where you can reach more than 5,000 meters above sea level, but still the average elevation is over 1,000 meters above sea level. Some peaks can reach even 3,000 meters above sea level. So all this westerly flow, moist laden airflow impinges over the Andes is forced to accept and produce this copious amount of precipitation in the coastal area, but particularly in the slope of the Andes. Now, these are phenomena that occurs in the day-to-day time frame. But when you look in longer time scale, for instance, year-to-year correlation, you find that actually the precipitation here is strongly correlated with the intensity of the westerly flow, precisely because when you have a year with strong westerlies, this year you have a lot of perturbations and a lot of weather system coming to the Patagonia. These years with the stronger westerly flow are those that have more precipitation. By the contrary, years with weaker westerly flow, they have less precipitation all over Patagonia. And this is shown here precisely. These are correlation in each grid point between the precipitation and the westerly flow or the zonal flow. And you see this band of red colors that indicate that the precipitation there is strongly controlled by the intensity of the zonal flow at internal time scales. And we see this also in other time scales. A year with more westerly flow will produce more precipitation. So in order to understand what causes year-to-year changes in precipitation, of course, the key is this westerly flow. But there are some large-scale phenomena that impact the westerly flow. What are these phenomena? The first one is ENSO, El Niño Southern Oscillation. And you know, most of you know that this is a natural phenomena that's alternate between El Niño conditions when the tropics are, the tropical Pacific is warmer than average, with La Niña conditions where you have a colder sea surface temperature in the tropical band. Of course, the tropics are quite distant from the Patagonia, but this warming or cooling of the tropical Pacific is capable to produce this rosary wave that's finally impact to the Patagonia. And indeed, here you have we can take all these El Niño years when, for instance, 82, 83, 97, 98, and more recently, 2015, 2016. And you can make a composite, and the contours here are what we call the 300 hectopascal geopotential height anomalies. It's kind of the pressure at the upper level of the troposphere. And the colors indicate the sea surface temperature. Of course, this is a composite, so you can see that during El Niño year, you have these warmer waters, colder here, not much action here right away, right at the coast of Patagonia. But coming back to the contours, the most important thing is during El Niño year, you have anticyclone conditions over the tropical Pacific, a low pressure center in the mid-latitude, and there is a high pressure, especially during the summer month, that sits precisely here in the southern tip of the continent. Now, this pressure anomaly, this positive pressure anomaly, produce this weakening. You can use the geostrophic relationship, and you can figure out that the winds tend to rotate in this direction, producing easterly flow anomalies precisely over Patagonia. And consistently, these years, El Niño produced, especially during summer, drier than normal conditions in Patagonia, because you tend to reduce, you have this Rossby wave train that tend to reduce the westerlies, and consequently you reduce precipitation. And that's reflected actually here when you look in December, January, February, the correlation between, we use the ENSO index to characterize the ENSO phases, and when you correlate this ENSO index with the precipitation in summer, you see this relatively negative correlations here over Patagonia. Not much in winter, but especially it's a summer signal that connects the ENSO with the Patagonia precipitation. The other large-scale phenomena that's modulate the precipitation over Patagonia is what we call SAM. SAM stands, I didn't put this here, but SAM stands for Southern Annular Mode. Another, this is a fashion in which the pressure field adjusts, and in different time scales. Typically from one month to others, you have these fluctuations in the pressure field. And one mode that's the atmosphere favor is this mode in which in 1 month you have lower pressure here over the Antarctic interior, a relatively higher pressure over the mid-latitudes. Remember that the pressure at the end is the sum of the mass of the atmosphere. So in general, these modes tend to compensate. You tend to have areas where you have more pressures and areas where you have less pressure. And one of these modes is precisely SAM. SAM has a positive phase and a negative phase. During its positive phase, the pressure, as I said, these are anomalies again at 300 hectopascals, the contours, and you tend to have lower pressure here over the Antarctica and higher pressure in this ring along the mid-latitudes. And again, that's tend to reduce during the SAM positive phase, that's tend to reduce the winds over Patagonia, and that's produce again the relatively dry conditions over Patagonia. Indeed, if you take this ENSO index and you correlate with precipitation, in fact, you find, and this happened year round, you have these negative correlations or regression over Patagonia. So SAM is up to some extent also another natural mode that's fluctuate between a positive phase and a negative phase. The positive phase is the one that's favor these anticyclonic conditions over the southern tip of the continent, reduce westerlies over Patagonia or North Patagonia, and subsequently that's reduced an anomaly, a dry anomaly in precipitation. So these are the two main modes that control the Patagonia precipitation. We have in the last year found another modes, but I will leave it as is with the ENSO and SAM. Let's now move to what has been going on for the last decades over Patagonia. Let's take a look of the climate change. This first figure shows for the globe between between the late 70s and the the beginning of this century. It shows the change in temperature all over the world. And of course, there is climate change, right? There is global warming, and most of the grid points are actually red, which means that they're having an increase in temperature. The exception has been basically the air temperature over the Southeast Pacific, along the coast of even southern Peru, northern Chile, extending all the way to Patagonia. So this period between 1979 and 2005, and this has continued for the next decade. So I can update this. I should update this. But anyway, the key point here is that in contrast to the most of the world, the coast of Chile, and particularly the coast of Patagonia, has exhibited a relatively weak cooling, not very strong. Now, immediately as you go to the continent, the situation changes and you have this warming. So depending where you are in Patagonia, if you are right at the coast, probably you have experienced relatively minor changes in temperature, perhaps slightly cooling. If you move to the Argentina Patagonia, for instance, you will find that the temperature has increased in roughly 0.2 degrees per decade, something like that. So not a very strong signal in temperature over Patagonia in contrast to the continental land masses, for instance, of the Northern Hemisphere or the rest of the continent. Not much going on in terms of the temperature. In terms of precipitation, we found, again, from the period the result doesn't change much with the period, but here I am showing the annual rainfall trends considered from 1960 to 2016. And you see these red colors here, each is one station, and these are the trend. And they are roughly 5%, minus 5% per decade. So there is a relatively strong and a significant a decrease in precipitation over Patagonia over the last decades. Here, just concentrating this panel, here you have the change both in terms of percentage and actual millimeters per decades. And you can see that this is for the southern box. You can see that year-round you have a decrease in precipitation. Now, it has been more marked, especially when you take the relatively amount, it has been more marked in summer. Less marked in March, April, May, in fall. Least marked, but still important during the winter month and the spring. So this decline in precipitation over the last decade has been the whole year round, but most marked during the kind of the warmer part of the year, summer and fall. And the question is, what is driving these changes in precipitation? Well, there are two drivers for the climate of Patagonia. One is the increase in CO2, in general in the greenhouse gases. But another very important is the decrease in the amount of ozone in the upper troposphere and the lower stratosphere over the high latitude of the southern hemisphere. These are the two things: the greenhouse gases and the ozone. How they impact the climate of Patagonia? Well, first of all, we can make this attribution not because we like these curves, but actually we can look in different models, and when you combine everything, all forcing, aerosols, greenhouse gases, ozone, this is the picture that you find in this model for the last decades of what is going on, and you can see the contours here are the pressure, and the shading is the precipitation. So when you took all the elements, you find that actually Patagonia has been drying. This is the red and yellow and brownish shaded that you find here. And this is because we have been basically this looks very similar to the positive phase of some. Some has a natural component, but also the climate change is some-like, and is positive some-like. You see that the pressure has been decreasing over Patagonia and increasing in mid-latitude. That's produced this weakening of the westerly winds, and that's produced the decrease in precipitation. So the models get this response. And actually, it's important, as I said, both the greenhouse gases, because we can make experiment with the greenhouse gases only, and it's also important this decrease in stratospheric ozone. You can see that's actually the addition of these two modes, or these two forcing, greenhouse gases and ozone, produce basically the whole response here. But let's go a little bit deeper in how these changes in ozone and greenhouse gases actually control the climate of Patagonia. Well, in normal conditions, you have a contrast at the level of the tropopause, roughly 12 or 15 kilometers high in the atmosphere, between a warm tropical troposphere and a relatively cool polar stratosphere. And that's produced a polar vortex. By the way, notice that here the South Pole is up and the North Pole is down. So here is Patagonia. So you have a polar vortex that's formed every year, and that's connected with the westerly winds at the surface. Now, over the last decades, what we have done is we have warmed the tropical troposphere precisely because we are injecting greenhouse gases, but we also, equally important, we have been cooling the polar stratosphere because of the ozone depletion. And are these two elements in concert, the warming of the tropical troposphere and the cooling of the polar stratosphere, that's produce a contrast in temperature that translates in a stronger polar vortex. This stronger polar vortex sooner or later also increase the winds near the surface. Now, to increase the winds near the surface, circling here the westerly winds circling the Antarctic Peninsula, or the Antarctic continent, excuse me, you have to have higher pressure at mid-latitudes and lower pressure at over Antarctica. And this is precisely the positive sun phase. So some or this some phase is instigated by these two elements, the warming of the tropical troposphere due to the greenhouse gases and the cooling on the polar stratosphere because of the ozone depletion. Now, this has been the process that explained the changes in precipitation for the last 4 decades or something like that. Let's go now to the future. The future is unknown because we don't know how much greenhouse gases we will put in the atmosphere. Of course, we can take different emission scenarios, one that's very pessimistic, that said that we will inject more and more CO2 in the atmosphere, another that's the famous or the infamous RCP 8.5, and others that are more benign in the sense that the emissions will decline, depending on this is the RCP 2.6. So depending on this scenario, you will have different concentration scenarios and different climate change. For matter of economy, we just look at the RCP 8.5, but remember, this is not a forecast. This is just a projection because it's contingent to the scenario that we're considering. The other thing that is what we have to keep in mind is that the greenhouse gases, regardless of the scenario, will continue increasing in terms of concentration, but the ozone is recovering. So maybe the last 2 or 3 decades ahead are not that bad. Well, it will depend on the greenhouse gases scenario, but at least the ozone will not play against Patagonia or against the drying of Patagonia for the next decades. Anyway, the models know that, but this is something to take in account and continue our efforts to reduce the ozone depletion. So what is projected? Well, you can take a look of different variables. Here I use some variables that I think that are important for people working in the kind of the biological component of this business along the coast. And for instance, these are the projected sea surface temperature changes. They are more marked, for instance, in the northern hemisphere and less marked in the southern hemisphere. This is kind of mimic what happened in the last decades. These are, by the way, projections for the end of the century under this RCP 8.5 scenario. So we expect an increase anyway of temperature of the order of perhaps a couple of degrees or less than 2 degrees here along the southern coast of Chile. More important or equally important are the changes in circulation, precisely because the sun phase will continue to favor the positive sun phase. We will see a reduction in precipitation that can be significant, especially in northern Patagonia. So again, similar to what has been going on for the last decades, will continue in the future, and we will see this continuation of the drying in North Patagonia and Central Patagonia as well, of again a few percentage per decade. Exactly how much, of course, will depend on which scenario of the greenhouse gases scenario we follow. Here it looks very brown because we are using the RCP 8.5. And of course, you can see in this model a variety of other variables. And here I am comparing different regions where aquaculture is taking place nowadays, southern Chile, Norway, Canada, etc. And as you see, we will experience the least change in temperature, in the offshore temperature. We also will experience relatively moderate or modest changes in surface salinity, but this is a region, in contrast to all over the world, where you in general tend to have an increase in precipitation. Again, this is a region where we will expect a strong decline in precipitation, and that's, that has important consequences for the local hydrobiology. Okay, so just to finish this, I don't know how much time has been going on. One thing is, again, talking about the mean, and we expect a moderate increase in temperature, a moderate increase in sea surface temperature, a relatively strong decrease in precipitation. But remember, these are the average for the end of the century under some scenarios. But over this average, you will continue having, for instance, El Niño years that in some cases can produce severe drought. So this is what I want to finish this talk, talking about the extreme events. And again, this is my example of 2016. 2016, we have a very strong red tide, harmful algal bloom that took place basically from February to March to May, and involved at least 2 species, right? And that has major consequences for the local economy, the local environmental conditions. We also, this year, we have wildfires and many other effects. And this was somehow determined, not all the whole story, but part of the story was this little rainfall that we get all the way from December to probably May or June, December 2015, January 16, February 16, etc. Here, probably this is a small figure, but anyway, these are the historical range of the El Pueblo River discharge, and we reached the lowest values in this austral summer, early spring, early fall. It was really a very dry condition that we experienced this summer. What caused this extreme drought in Patagonia? Well, in one hand, we have a strong El Nino. We have a peak of El Nino activity in summer of 2015 and fall of 2016. It was actually comparable to the big El Nino of 1998 and 83. So in one hand, you can say, oh, it was El Nino, and this was a natural component. But also, as we discussed before, this is the SAM trend or the SAM values, and you can see how the SAM has been going on, this upward trend, and in fact, 2016, it reached a very high value. This combination of El Nino and positive SAM phase of SAM, we haven't seen much of these cases in the past. But it's plausible that climate change is producing these SAM, positive SAM conditions, and over this, you can have either phase of an ENSO. So it's important to be prepared. We not only will have this decline in mean precipitation, but also we can have these extreme events. And we have good reason to know that deficit in precipitation translate in harmful algal blooms, like the one that we have in the year 2016. So be aware of that. In fact, some papers, this is one from my colleague Rodrigo Aguayo, people has already begun to quantify these extreme events, and there is a mean drying. Here you can see different projections. So if you take the 50% value, you see how this median value will decrease in the future. But this shows how these extreme events, like the March 2016 discharge in the Pueblo River, in the current day, it occurs less than 2% of the time, but in the future scenario, it can be up to 6%. So it can duplicate. Still is a small value because it's an extreme event, but it can be double or occurs twice as frequent as occur in present day. So my conclusions is that climate anomalies are accounted by changes in the westerly wind impinging the austral Andes. We don't know much what are the drivers of temperature. Large-scale circulation anomalies are in turn modulated by ENSO, which is mostly natural, and SAM. SAM has a natural component, but the trend is completely driven by anthropogenic forcing, greenhouse gases, and ozone depletion. There is a robust projection, changes in precipitation, and somehow in temperature, but particularly this decline in precipitation. And this is precisely what we said here, right? Dry in central Patagonia plus warming, and superimposed on natural variability that can bring these extreme events. So that's conclude my presentation and ready for respond any question about that. Thank you very much.
Thank you so much, Dr. Garreaud. We have an interesting question for you.
You are still there.
Yes, we are. And I have saved some applauses for the end as well. Are atmospheric rivers more frequent today in southern Chile? And what effects do these rivers have in northern Patagonia? No, sorry, we cannot hear you. No. No.
Technology is failing.
Oh. This is a shame. We are really sorry about it, and considering we are. Oh, I see you are writing your answer in the chat. So we can, as said at the beginning, we will forward the questions to the different speakers, so we can have some of their responses. We can share with the participants by email. We are really late, but we are very satisfied with this seminar, this workshop. I have a hard time thinking of a workshop with a variety of high-level keynote speakers. Usually one or two. Today we have had 7 very good keynote speakers. I will not take the risk of trying to summarize, but it's certainly clear that in order to address the challenges we are facing in southern Chile, in Patagonia, we need to start integrating the biological sciences, climatic science, social science, political science, and so on, and also to integrate the knowledge and the decisions from all the communities and actors that participate in the real world. Just a few comments. All the presentations will be soon available in the web page. The videos which have been recorded. And would you like to say a few words, Dr. Buschmann?
No.
No, okay.
No.
I don't know if you can hear me now.
Yes.
Okay, I don't know, probably I hit something. Excuse me for this, but anyway, I know that it's late, and I will be happy to respond the question offline. So if there is anything about ARs, atmospheric rivers, or climate change, I will be happy to comment on that.
I think you have the right to respond. I will repeat the question.
No, I hear that. Thank you, Andrés. No, I just wanted to say that it's a little bit contradictory, because we have seen this decline in precipitation, but we have observed this higher frequency of very powerful and destructive atmospheric rivers. This year we have a big event, I guess, in the middle of May, and that's produced these big problems in Termas del Amarillo. People disappear on that, and every year we see this. Now, sometimes this happens in science, right? You are not aware of some phenomena, and then you discover, or you visit this phenomena, and you start to see this more frequently. So we don't know yet if there is an actual increase in atmospheric rivers that are really powerful and destructive in some places, or this could be just an artifact of our detection system. So we are working on that. And maybe these two things are not necessarily contradictory. I said that isn't a contradiction, but maybe you can have stronger events, but in average, still the precipitation is decreasing. So keep in mind that two things can happen at the same time, and both will have an impact on the biology and hydrobiology. Both the drying and these very extreme events, I'm sure that they produce something.
Okay, thank you very much. Not all of the presentations will be available, but the videos will be there. I want to thank all the speakers, all the participants, which we have reached a peak of about 100 participants, and now we have nearly 40. So it has been a great success for us. So applauses for all of us. Thanks for the patience. And we look forward to meet, hopefully in the near future, here in Chile, in southern Chile, and also having the chance to enjoy some of the great seafood we produce here, and some of the good wine we produce a bit further north. So thank you. Good evening, good night, good morning. I don't know anymore, but Dr. Buschmann wants to say.
Well,
something.
Thank you all for participating, and we will meet in some days. I will go over all your responses tomorrow, and just to discuss what is going on in the Patagonia and try to come to some recommendations for our society here. It's complicated. There are many crosses and the response are not linear. So I hope that we can do something interesting in that discussion. So thank you, everyone.
And thank you to the staff providing the platform for meeting, for ID. They did a great job.
Yeah.
So thanks everyone, and hope to see you soon.